Perfect. Good morning, everybody. Thank you for joining us today for this class, air sealing class training. I just want to give you a quick Zoom orientation, like you were hearing us discuss. If you have a question, we will either take your question one of two ways. You can either raise your hand. If you click on participants, you should have that option to raise your hand. If for whatever reason that doesn't work, then you can definitely use the chat function, and we will take care of your question. Like I said, Ian will kind of bring it up and bring it up to Terry, and when he feels it's right when we're talking about the subject, or whenever we have a chance to ask Terry the question. Next slide. Ian, can you give me the next slide?
Working on it. Seems to be some issue.
Animated slide so you can see the instructions on how you can raise your hand or do the chat function.
Oh, here we go. Let's just do this way. Excellent.
And I just want to give a quick introduction about what is a Tri-County REN, or what you often refer to as 3C REN. So what 3C REN is, it's a regional energy network, and it's the counties of Ventura, Santa Barbara, and San Luis Obispo. And what you've probably been familiar with utility programs, different trainings that they offer either at Edison or PG&E, either in Irwindale, Tulare, or San Francisco. But what the three counties decided to do is to bring those trainings into a more local region. So it's a ratepayer fund, and we applied to the Utilities Commission. And we said that we felt that we needed more localized and regionalized training here. We don't have the opportunity to travel to LA or San Francisco, and we wanted to have that offering to our local workforce and residents. And what we have is 3 programs. If I can have the next slide. We have what the one that you're currently taking the training for is building performance training, and then we have an Energy Code Connect, and we have a home energy savings program. And what building performance training is, the one that you're currently getting the offering for, is offering different training to our local workforce and tons of different topics. Here listed are a couple of the sample topics that we've offered or we're planning to offer in the upcoming months, the end of this year and coming next year. As you can see, it's anything from zero net energy to local, soft skills, business development, to realtors and offering green designation that they also are interested in. So if you are interested in suggesting any type of topic that you feel it's beneficial for a local area, or something that you haven't had before, or something that you've heard the utilities have offered but haven't had the chance to attend, please let us know, and we can certainly try and figure out how to bring that here locally. Next slide. And then our Energy Code Connect. What that is, we have regional forums and also training, and this is with everything having to do about the energy code and green building standards. And then that's either through trainings just like this one, or we also have regional forums that we host maybe 2 to 3 times a year. Currently, it's a little on the virtual side, so we're not sure how often we're going to be offering those moving forward. Another good benefit about the Energy Code Connect program is we have a hotline. So anybody that has the questions about energy code, we have a number that you can call, and you get personalized service about energy code. Any project that you're currently working on, we have somebody that can offer support and advice on those energy code questions. And then our next program is home energy savings. And what this is residential energy efficiency retrofits for homeowners. Currently, everything's being done virtual, but we can offer a virtual home assessment. We offer a free starter pack with, has LEDs, power strips, and different things that you can self-install at home. Hopefully, once we're able to go back into people's homes, we can have more deeper savings and deeper retrofits. We also have a copay option for that program. And there's a lot of different measures that we offer, and you can check our website for more information on that. And I will now like to introduce our class and our instructor for today, Terry Norby. Terry Norby of Air Sealing Solutions has been a general building contractor for over 40 years. In 2009, he also has been and currently is still active in Passive House. In 2009, he assembled California's second passive house retrofit. And in 2012, he built California's first new construction of passive house. Currently, he consults with architects, designers, contractors, and builders on how to achieve high-performance buildings with zero net energy targets. Also, you can probably also, if you have any access to home energy magazines or any journals having to do with constructions or zero net energy, you've probably seen him. He's also been a writer for Home Energy Magazine, Journal of Light Construction, and he's also presented at many conferences around the US. He is currently in the Marin County Architectural Commission, and he's been there for about 5 years. And he is in the middle of writing a book about air sealing and wood frame buildings. So that's something that we will have access to once he's finished with that book. So thank you once again, everybody, for joining. Terry, if you can start your class. You're on mute.
I'm not on my screen yet. So good morning, everybody. I just lost connection for a minute, so I'm not sure what happened in the previous 3 minutes, but I sincerely want to welcome you all to this. These are really, really valuable trainings. 3CRN gets some of the top people in the country to offer free expertise on building related stuff. And tell a friend to tell a friend, because these are very valuable classes that are just hard to find anywhere in the country. So you just kick back, turn on your screen, and I'm going to try and introduce you to the real true value of air sealing in buildings, which I only discovered about 15 years ago. So back to my staff. I don't have my screen on the picture. I mean, on my PowerPoint is not up yet. So can you guys help me out there? I'm not on.
If you could hit the share screen.
Okay. Share screen. That's right. There we go. Sorry, I forgot that step. Okay, good. Here we are. So again, welcome everybody. I just want to do a check. Is everybody out there can hear me, and all of our sound communication is good? Yeah?
We can.
Okay, good. So air sealing wood frame buildings. When I say buildings, I mean houses. California predominantly is stick frame, wood frame buildings. The suburbs, 95% of the suburbs are wood frame houses. And particularly what I'm going to try and emphasize a lot in the show is retrofit air sealing, because air sealing a new building, once you have the techniques and the inspiration, air sealing a new building is fairly easy to get it to any level of tightness you desire. Retrofit air sealing, however, is extremely challenging, and it can be cost prohibitive, or it can just be access prohibitive, where you cannot achieve high air tightness in retrofit. But I will show you all the tricks of the trade that I have learned over the last 15 years on air sealing new and retrofit. So with that, we will get on with the show. Oh, a little intro. So Alejandra told you a little bit about myself. Basically, the way I got into air sealing was about 12 or 13 years ago. I was asked I won a bid on a retrofit remodel out where I live. And one of the requirements was that the house had to be airtight. And up until then, airtight was not in my dictionary, nor was it any of the builders I knew. Air sealing was not in the vocabulary of construction 15 years ago, even 12 years ago. So I went at this building and it just had to be as airtight as possible. But by the time we finished, I was somewhat obsessed with air sealing. It just seemed to be my thing. It's like, it was such a newness in construction for me that I just dove into it, and I've been kind of on that path ever since. And I'm going to share with you all of my learnings of the last 12 or 13 years. So here we go. Why make a building airtight? Good place to start. So these are testimonials. This is just like testimonials of why air sealing buildings makes sense. So Lawrence Berkeley Labs, they're kind of one of the big national big hitters for figuring out how to make better buildings down to the fine tuning of the mechanics and physics of good buildings. Air sealing is finally emerging out of hiding as being recognized as one of the three most important things we can do to make our buildings work better and save fuel. You would think on that alone, you would just go, okay, that's what I want to do. But let's weigh in with some other people. Well, I'm not advancing here. Let me see. My slide is not advancing. Let me try something else. Oh, there we go. Okay. Zero Energy Project, that's a big national coalition of a lot of people involved who are trying to get zero energy happening on the planet, but particularly in North America. Here's one of their quotes. Super sealing the building envelope is the single most cost-effective measure builders can take to improve the energy efficiency of a zero energy home. Again, you read that and you go, okay, that's what I want to do, you know? We're always trying to do in cars and phones and computers and TV, in all parts of our life, we're trying to, the human endeavor is to make the next best thing. Unfortunately, we haven't advanced that much in our buildings. And now we're realizing that air sealing is one way we can really advance the cost effective and the energy use of our buildings. One more testimonial. John Straub, buildingscience.com. If any of you don't know about buildingscience.com, jot it down and check them out. They are the global authorities on building science, basically. And that's what this is all about. Excuse me. The new movement into better buildings is based on building science, and building science is based on basic laws of physics, really simple stuff applied to buildings. Approximately 30 to 50% of space conditioning energy, 30 to 50% of the energy you pump into your building, heating or cooling, is lost due to air leakage. Again, you read that and you go, okay, I'm not going to do that anymore. A testimonial. Department of Energy, the big boys, the big guns, national big guns, they say a tight house will have lower heating bills, have fewer drafts, potentially require smaller heating and cooling equipment. This is, I don't agree with this. They absolutely require smaller heating and cooling equipment. RDH building site. RDH is a big national company that only does high performance, energy efficient, zero net energy passive buildings throughout North America. And excuse me, and they do anywhere, pretty much they do commercial stuff, high rise, apartments, multifamilies. Quote from them, simple, a leak wastes money. Pretty simple. So there's a couple of testimonials as to, you read that and you go, okay, let's do that. This is a place we need to go. It's really that significant. It's not a secret anymore. So now we're going to start with the basics of air sealing and what is air sealing. What we're looking at here is a balloon, obviously, and then outside the balloon, excuse me, is the envelope, a building envelope. The squiggly lines are insulation, and on either side of the insulation is a solid line which represents the framing, the envelope of the building. So what is this? Up in the top left here, in big bright yellow and orange, I made these bright because this is what this slide is all about. There's something called the pressure boundary. It can also be called the airtight layer. It can also be called the control layer. I like to call it the balloon skin because it's also that. And for me, when you're describing, as we're rolling through these slides, I will be mentioning the balloon skin because the balloon skin to me is visually an easy thing to see. When you say a control layer, you go, well, what is that? Or what's an airtight layer? But when you say balloon skin, you go, I know what a balloon skin is. So let's do the balloon skin in the house here. This balloon skin, you go all around it, has no holes in it, and it has the ability to keep a different pressure inside than outside. Different pressure inside and outside. So the skin of the balloon is the pressure boundary. Inside is high pressure, outside is low pressure. It's also, the balloon skin is a control layer, so that remains to have to stay that way. It's also called the airtight layer, which is pretty obvious. So you know what the balloon does. All we need to do is employ that in our buildings. So let's go around the house. Start the roof. Let's say this is a cathedral ceiling roof, and the airtight layer, the control layer, the pressure boundary balloon skin is on the roof, the plywood, the OSB, right? We air seal that. Air seal, air seal, air seal. We come around the building, and then we come down the sidewall here, and we have an option here for air sealing. We can go inside the building, which typically most houses are. If you look up in your house, the ceiling above is the airtight layer. That's where you do the air sealing. You go up into an attic and you air seal the attic so you can get this airtight. But let's go back out here. So we're going down the roof. We have an option of going inside for air sealing, or the roof can be the airtight layer. We come outside the building, airtight. The window assembly is part of the airtight assembly. Windows should be airtight. Come down the sidewall, and then we jump inside the building again, and we're on the floor level. We can air seal the top or the bottom of the floor, doesn't really matter. And then we jump outside the building, we go up, and we start all over. We came back to where we started, and that's our balloon skin. That's basically what air sealing is. We want to do the balloon skin in our house. And we'll get to a lot of people worry, you can't do that. You'll suffocate. You cannot live in a house that's that airtight. But guess what? That has changed. We can live in an airtight house with better air quality than in a leaky building. And hopefully we'll get to stick around for part 2, and I will explain fully how we can have airtight houses and fabulous indoor air quality. So just keep in mind, that's the gist of air sealing. Airtight, control, pressure boundary, balloon skin. Excuse me a sec. This crude drawing I made is another illustration of, this is an illustration about punctures in the airtight layer. So this yellow, all this yellow around the building here, actually I'm gonna grab a, no I won't, okay. The yellow all around the building is the potential airtight layer. And the cathedral, this is the cathedral ceiling, that can be the airtight layer, right? And then you go down the sidewall, just as we had in that previous slide, airtight layer, the floor, back out. So you go all around the building, the balloon skin, that's a potential airtight layer. But because we're not married to one airtight layer, we can go inside and have the drywall, and the interior walls can be part of the airtight layer. So this is just illustrating potential airtight layers, but the circles are illustrating what we do to the airtight layer in terms of holes. These circles are just about wire holes and plumbing holes that we make in buildings. In a drywall ceiling, we put a light fixture and we make a hole in the airtight layer. In the partition walls, we drill holes in the top plates of the partition wall, run wires and plumbing, and we introduce air from the wall up into the attic. So these are all punctures we make in buildings. Here's a hose bib connecting outside air to the inside. These are punctures all buildings have. All buildings have these. We're finally getting to a point where we realize, wow, we really do have to seal these. You go back to a building 40 years ago, none of these were sealed. We're getting better at this. So something I realized, you know, everything, all our discussions in air sealing is about a hole. You go, well, what is a hole? You know, so a hole it's not a one-way valve. A hole in a building is not a one-way valve. Air can move in either direction through it. If the wind is blowing outside, if it's a 40-mile-an-hour wind, you have a high pressure outside, air is going to go through that hole for sure, beyond a doubt, into the low pressure in the building. Or in reverse, if there's high pressure in the building, it's going to go out. If you have a kitchen hood fan running at 300 CFM, it's going to suck in outside air, create from the negative pressure inside. Just know though, when you see a hole, air can go either way, depending on the conditions. Another thing about a hole is when stuff moves through the hole, air moves through the hole, moisture goes with it, not just heat or cold, but moisture goes through it. So if you're trying to control mold, indoor moisture, holes are not a good idea because it's a wild, free run of the outdoor environment to come into the house. Hot to cold, humid to dry, will go through that hole in either direction. And it goes through faster. This is key here. The environment and the conditions go through holes faster than any other building part. You think about it. What can go through, exchange the outdoor air from the indoor air faster than a hole? It'll go through insulation or even materials slowly, very, very slowly. But a hole is a high-speed runway for the conditions to move in and out of. Enough about holes. What kind of leaks? So I broke leaks down into two leaks. There's a source leak and a peripheral leak, or a secondary leak. A source leak is any hole in the balloon skin, the airtight layer, right? You have an exterior plywood, you make a hole in it, that's the source. One side of the hole is the environment, and the other side of the hole is introduction into your building. It could be insulation, or it could just be the inside of the room. Holes in top plates in the attic. Why would a hole in a top plate be a source leak? Because it connects from the attic directly to the wall, which is part of the conditioned space. And the attic is what I call wild air, is anything outside of the building envelope. So the attic is very wild air. The attic will heat up to 120 when the sun's out, or it'll go down to 32 when it's a few days of cold weather. The attic will assimilate the cold weather. It will become the cold weather. Peripheral leaks, or very often, this is good to end confusion. When you're seeing leaks, what are you looking for, a source leak or peripheral leak? If you have a blower door and you're testing a building, you might get air leaking out of outlets, switches, baseboards, holes in bottom plates, holes in drywalls. That's not the source, right? If you go back and if you can seal the source leaks, one source leak can shut down 5 peripheral leaks. So it's always preferable to air seal at the pressure boundary. And it's always preferable to know where you are. If you're feeling air coming in, is that the source, or is it just coming in from the source, which might be 10 feet away? Dicey transitions. This, if you remember the earlier slide where I showed how the blue here represents the potential airtight layer, the pressure boundary of the balloon skin. So again, if we take this blue line around the building envelope, and that's airtight, whatever heat happens in here can't get out through those superconductor holes. So that's what this blue line is. So this represents a crawl space, a section of a building with a crawl space and an attic. So we have chosen the airtight layer to be the attic ceiling. Then it suddenly has to go out of the attic to the outside. It could go inside, but this case we're showing it goes, because this is typical, the air seal will go from the attic to the outside, down the outside, and then typically run back in the house to the floor, as we showed in the previous slides. So this is very typical assemblies. There's different ways to choose the airtight layer, and there's different assemblies, but this is very, very typical for a stick frame construction in a ranch house, let's say. So what we're looking at, all these circles, this circle represents, you have to go from when you have to go from the outside of the building to the inside, that's tricky, right? How do you do that? It's a complex assembly up there. And in retrofit work, it can be extremely complex. So to continue this blue line, the balloon skin in, you have to have an understanding of the anatomy of the assembly you're looking at. Same with the bottom. And if it's on a slab, it's in a slab, the bottom of the slab floor is airtight and the outside is airtight. But one little hole, this is very, very typical in all buildings. The exterior sheathing or plywood doesn't sit flat on the building, and air gets behind it. And once the air gets in, this is a slab, it can go under the plate, over the plate. Once it's in there, it can go under the baseboard, behind the drywall, and a hole in the drywall. This would be an outlet. So these are secondary leaks. Here's a primary leak. But this, all buildings do this. Any building on a slab will do this. Some places more, some places less, but they all do this. So these dicey transitions from the outside to the inside are things that you really need to study when you're designing an air sealing in a building, because this is where you're going to have trouble. This is where you're going to have leaks. If you're in a retrofit and you're looking for trouble and leaks, this is where you're going to find them. And this is where it can be really, really difficult to air seal. What I like to do is study, when I'm doing work, is study one of these transitions in the job that's in front of me, write it down on a piece of paper, and then I have, in my mind, I have a pathway, an idea for the balloon skin. And then I can hand that piece of paper to one of the workers and say, okay, this is how we're going to air seal this. Stack effect. I call it accelerated heat loss. So I know there's a lot of, apparently there's a lot of contractors and maybe some engineers and architects, designers out there who I'm sure are probably familiar with stack effect. I'll go through it a little bit and explain how stack effect really is more than just a pretty picture of the top of a building billowing out. Stack effect is accelerated heat loss. That's what's important about stack effect in my mind. So here's a drawing. My son's an artist, and I gave him a section of architectural drawing of a stack effect, and that I drew. And I said, "Can you draw it?" And he drew this comical, I like it, picture of stack effect. So here we go. Here's stack effect. I showed you earlier that blue lines here are holes in the bottom of buildings that all buildings have. I've never seen a building that didn't have holes at the bottom in different places. And the orange is all the holes at the top. Again, I've never seen a building that didn't have holes at the top. So buildings have this, holes top and bottom. So no big deal. If it's 70 degrees outside and it's 70 degrees inside and there's holes in the building and the wind's not blowing, it doesn't matter. Nothing's changing, nothing's moving. The heat's not on, who cares? The air conditioner's not on. The building can breathe and leak. But that's not what we're concerned about. We're concerned about fuel, combustion, climate change. Basically, the bottom line is combustion. We want to stop or eliminate or slow down the burning of fossil fuel. And we can do that, as previously stated, by air sealing. So we're back in the building. Let's say it's 40 degrees outside. You want it 68 degrees inside. You turn the heater on, right? And the heat's rising as it does. It's lighter. It's less dense in the cold air. The heat rises, and as it goes to the top, guess what? It's going to want to go out all these holes, right? And as soon as that starts to happen, it starts sucking in cold air from the crawl space outside. What if there's rodents down here? That stuff, that odor is coming right up into the house. So this is what stack effect is. You turn a heater on, you get a certain sweet spot, and all of a sudden, boof, you kick in this accelerated heat loss. The heat rises, it sucks cold air in, and you get warm air escaping out. This is expensive. This is money. This is fuel into the building and going out at an accelerated rate. I'll show you what accelerated means in the next slide, I think it is. No, it's 2 slides. So that's basically what stack effect is. And it happens at the dumbest time. Stack effect happens when you're heating or cooling, right? So here is this right here, QC. This is the formula for stack effect. There's a few variations of it, but it's a global formula for stack effect that's used in industries all around the world. It's a basic patent formula. But I'm not into the nerdy kind of stuff. So I don't really care about what all that means. If you really need to know, over here is what these values are: flow rate, constant, discharge, stack height, temperature. Basically, for our purposes now, all we need to know is stack is guided by 3 basic elements: indoor-outdoor temperature difference, which, like I said, if it's 70 in, 70 out, there's no stack, right? hole sizes, typically at the top and bottom of the container, and the height of the container. Height is really important. The higher it gets, the faster, the more accelerated stack happens. But that's basically what stack is. Temperature difference, hole sizes, height of container. Here's what stack does inside a building. It stratifies the temperatures inside the house. As we saw, when this heat comes up, this is hot up here. This could be 72 degrees up here, and you could be sucking in, 62 degrees here. So it's cold here, hot there. You're trying to be comfortable in the middle. Cold air is going across your feet, and your cheeks are red hot from the heater because it's 10 degrees warmer up in the room. Stack increases every time the heat is turned on. All buildings have it. I have never seen a building that didn't have holes in it. And if a building has holes in it, top and bottom, it has stack. Our ancestors, our grandmother and grandfather raised us in buildings with stack. That's all we're used to. It's changing. I build houses now and involved with houses that don't have stack. And the comfort inside is phenomenal. It's just something we're not used to experiencing. Airtight houses have little to no stack. Stack effect makes thermal comfort challenging. So here's the set in motion. Here's the stack formula, set in motion. The formula's up there. And I'm gonna try and move this aside. And so here's what we got. We're inside. This thermostat is set at 70 for those of you who like it warm. Outside, I'll give you the outside values, temperatures, they vary. The vertical bar here on the left goes from 0 to 400. Those numbers are cubic feet per minute. So 200 is 200 cubic feet per minute. A cubic foot is about, let's say, the size of a basketball, right? So this is 100 basketballs, 200, etc. Across the bottom here, we have the variable temperatures outside. Inside, we know it's 70. Outside, it goes from 60 to 30, colder. So look at this. Now, this is pretty cool. So at 60 degrees, the accelerated air leakage is 160. This is kind of hidden for me. Let's say 170 CFM is being quickly shot out of the house just because of the temperature difference and the holes. If you let's go all the way over here to the left at 30 degrees, same conditions. It's just colder outside. The holes are the same, the thermostat's the same. It just gets colder. And suddenly we're losing 340 cubic feet, 340 basketballs a minute out the holes. That's phenomenal. It's just amazing. But that's physics. That's science right there. You can't say, nah, I don't believe that. That doesn't seem right. That's physics right there. That's what stack effect is. And that's what happens in our buildings. Of course, there's variable in buildings because buildings are not perfect cylinders and tubes. So you debate that, it's not really fair because a rectangle house is not a cylinder. But let's just use this as a takeaway. Stack effect really affects heat loss in our buildings. Oh, this little thing here, delta T. For those of you who don't know, I might go mention this. What delta T is, basically, it's the difference in temperature between one side and the other. In the case of a house, it's between the environment and the indoors. So the delta T in this slide would be the 70 degrees inside temperature, and the delta T would be 55 degrees on this one outside. That's basically what delta T is. Pause a sec. Opportunities for deep air sealing. So this is important because if you're planning or thinking about doing anything to your house, it's important to think like, wow, okay, air sealing is important. I really want to do it. It's really important. For all the reasons you want to do it. So the biggest bang for the buck come from these opportunities for deep air sealing. I underline deep because you could just go around your house and weatherize it and put new gaskets around and spray some foam. That's not deep air sealing. The deep air sealing that we're going through today is, I'm going to be showing you how to air seal a building from any level of air tightness you want, from very, very tight for right now to, that's my level. That's the only level I do. Very tight to super tight. That's what I'll be showing you. So this is opportunities for deep air sealing. Putting on a new roof. Once your roof is off, you have access to the attic. You just knock some holes in the roof. You can go in the attic, pull out the insulation, and get access to the air leaks in the attic. It's a huge advantage. And you cut out, if you can cut out the stack in the attic, you can cut an enormous amount of leakage out of your building. Number one place to attack air sealing is in the attic. And you have to remove the insulation to do that. Crawl space, similar. New attic insulation, if you're taking the old insulation out, golden opportunity to air seal. New siding taking off, another golden opportunity to air seal the vertical sidewalls of the entire building. Or vice versa, if you're inside and removing drywall, that's another golden opportunity to get at the air leaks. Window and door replacement, if you remember, I said windows and doors are part of the airtight layer. If you're replacing doors and windows, you can make a dent, not a sizable dent, but a dent in the air leakage of your building by making sure the new ones go in or installed in an airtight way, and that the windows and doors themselves are airtight. So how much does my building leak? Let's see, blower door. So I'm just going to briefly go over blower door. I don't know how many of you, if we could get a poll, I'm just curious if people could just kind of write in and just say, I own a blower door, I've used a blower door, or I have no experience with it. I'm curious how many people out there involved with blower doors. I know your HERS raters are, and but I'm just curious, know what blower door usage is in our audience. So blower door, whoa, I jumped ahead there. So here's what a blower door is. I say put a face on air sealing because the blower door is really less than 30 years old. And 30 years ago, there was no quantifiable way to tell how much a building leaked. Nobody knew, right? You could feel it, but you never really knew it. The blower door suddenly came up with this device and it said, aha, we now have a way to put a number, to put a face on leakage in buildings. So here's what it is. In the center here, center shot, you basically are going to test a building. You put the building in winter mode. That means all the doors and windows are closed. Everything is closed up. You pretend like the heat is on. You don't want any of the heat to get out. So you put your building in winter mode, and then you open up one door or a window, and you put in this shroud, this nylon shroud that fits very airtight in the door or window opening. At the bottom of the shroud is a large fan, right? That's controlled by this this monitor on this speed control on the wall, and you have the option of having this fan blow air into the house to pressurize it, or you can flip the fan around and you can suck air out of the house to depressurize it. The pressurization or depressurization is measured in something called pascals down here, and pascals is just, for some reason, it's the universal measurement that's used throughout the world, the unit of measurement for pressures, negative and positive. So blower doors use pascals as a measurement. So get the house tight, put this thing in, turn the fan on, and in this case, we're sucking air out of the building. This happened to be a 3-story building. This was a 3-story condo in San Francisco. We actually got this building down to less than, to about 1/2 air change per hour. And this guy here was the designated, I worked with him and his crew, and to make sure that throughout the assembly, we were on target and doing the right things to make this building airtight. It was quite a struggle. It was very expensive, but we did it. So turn the fan on, negative pressure, and what he's holding in his hand here is this thing on the left. It's called a manometer, and it's basically a very expensive, high-tech pressure gauge. It's a pressure gauge. So you turn it on, and on the left side of the screen here, it's reading the negative pressure in pascals. 50.0 is 50 pascals, which is the universal test measure throughout the world. It's a baseline measurement for air leakage. On the right here, it shows the actual CFM that's leaking out of the holes through some magic. It's a calibration of the fan speed, the fan opening, and the pressure difference between indoors and outdoors, and it comes up with this number. I have no idea how it does it. So we're at 50, so we turn it on, and suddenly the pascals are going from 30 to 40, and you hit 50 pascals, and the building is at 50 pascals. You push this hold button, and it locks in the CFM reading. That's basically what the blower door is. That's what the manometer does. It's pretty much that simple. Of course, it can get a lot more complicated. So we got 50 pascals, we locked in the reading, and not this building, this is some other building, was leaking 2,175 basketballs per cubic feet per minute under this certain pressure. That's it. That's what a blower door test is. Now, when you turn in the papers for your homework and for your reports, usually these readings are given as air changes per hour. It's cubic feet per minute, but the papers are going to read air changes per hour at 50 pascals. So this is a universal number we're reading here, unless you're doing surface volume leakage. But this is, surface square foot leakage. This is volume leakage. So that's basically it. The ACH 50 is air change per hour of 50 pascals. And there's a formula, where is it? Down here. Here's the formula to convert cubic feet per minute to air changes per hour. So I'm not going to spend too much more time on blower door. It can be as complicated as you like, but this is the go-to test thing for all buildings throughout the world to see how much they leak and to actually fix leaks while they're leaking. I can explain that later. Now, here's a little footnote. 1 cubic foot, one basketball in a minute is equal to about a 1-inch hole, for reference. So this kind of jumps away from blower door a lot. So this is a significant slide. So now do you know what ACH is, air changes per hour? I might be able to explain this slide. So this is the number of solar panels needed for zero net energy for, let's say, a boilerplate house. We don't know what the house is, what the building is. It's just the number of panels needed to zero out the building in relationship to the air tightness. So this is all about the relationship to air tightness. So go down to the bottom here, 5 ACH, which is a very, very typical building leak. Right now we're building at a very tight building, might be 2 air changes an hour. Zero net energy is sort of requiring that buildings should leak 2 air changes an hour. Passive house is required. The building cannot leak more than, let's say, a half an air change an hour for new construction and 1 air change an hour for retrofit. So that's very tight. 1 air change an hour is really tight. 5 air changes an hour is typical. And 2 is, let's say, zero net energy. I test buildings that have 15 air changes an hour, 10, very common. So anyway, back to the gist of this slide. So if you take a building, let's say 2 air changes, a zero net energy building, here's the size, the usage, the boiler, whatever these boilerplate numbers on, at 2 air changes an hour, it would take 20 panels to zero it out with that much leakage. At 5 air changes an hour, it would take 60 panels. So just breathe that in for a minute. Passive house, at 6 air, 0.6, 14 panels to zero it. So we go from 14 to 60 panels based on air leakage alone. How air gets in or out, the anatomy of an air leakage, This is just kind of stuff you've probably all seen, but I want to show you why it's significant. This picture here, a friend of mine, he's a high-end builder. When this place was all done, it would look gorgeous. Custom windows, $2,000, bathroom sinks, and a lot of marble and granite and high-end stuff inside. But if you can see from the outside, in terms of building science and air leakage, this is total crap. This is just unacceptable bad behavior. But the contractor had no idea. And these are the buildings that wind up leaking 10 to 15 air changes an hour. You put siding over it, #1 shingles, very expensive, with tar paper. This thing's going to leak like, I didn't test the place. So here's a 90-year-old building, or 61-year-old leak. The old board sheathing floor, before plywood. We used board sheathing with the gaps in them. So this is about source leaks. Holes in the floor down to the crawl space, that's a source. Crawl space is wild air, comes right up into conditioned air. That's a source leak. But that air can wander around and wind up in an outlet, and it does, and it will. There's more source leaks into the crawl space. Now you cover this stuff up with drywall and baseboard, and it's going to slow it down, but you are not going to stop these leaks. These leaks are definitely going to show up in all of the outlets and the valve stops here. They're all going to show up. So this will illustrate. This was a job I was just doing air sealing consulting on this, and I came in. The contractor had demoed, took out old drywall in this. This was a walk-in closet and bathroom, and I looked at this wall and I thought, whoa, that is centerfold material. And so what I looked at was, of course, not what my mind saw, because I'm an air sealing nut. I saw the pathways for air leakage. All this yellow spiderweb, mycelium of air behind the walls, is pathways for air to wander around behind the wall. Behind the drywall, hole to hole, air can come up here and wind up coming out here in this outlet. The source leaks are these hole in the floor, these holes, that's a source leak. There's also source leaks up in the attic, which you can't see. But those source leaks can feed all of this stuff behind the walls, and they can come out of outlets, valve stops. You put these silly little escutcheons over the valve stops. That's not airtight. This is where the air is going to come out. Secondary leaks, source leaks, hidden behind a wall. And when it's all done, how could that leak? It looks pretty tight to me. Here's more visual stuff, leakage. Typical, all houses, most houses have panels, sub-panels inside the house, and the wires go up into the attic. These typically are unabated, unsealed holes. We're now doing these finally with can foam. Fireplaces, massive leaks all around them. Because masonry is not allowed to touch wood, there's an air gap all around the fireplace, and that air gap is attached to the walls of the house, let alone the big hole that goes up out of the top. Bathtubs, any bathtub with a crawl set on the first floor with a crawl space under it has a hole in it this big. This is the way they do the plumbers. They just take a case, make I think it's a 13 standard hole, 13 by 8-inch hole and they set the tub on top of the hole so they can go into there and hook up the tailpiece and stuff. The wrenching on this. Direct hole, crawl space to living space. Here's a remodel box and drywall. Look at the ability for air to get from the outdoors indoors, and you put a cover plate on this, and you'll slow down the leak, but you will not stop these leaks. More holes in the bottom plate into a crawl space. Holes in this is really a crazy story. These holes here, so much work is done based on tradition, not on thinking. So these cavities here were going to be insulated, right? And so whoever was building this, they called me an air sealing consultant. So whoever was building this said, well, you have to vent, every house I did had vents on the eaves. You have to vent them. So they drill holes in an insulated air cavity, which is crazy, really nuts. You do not ventilate insulation. It works against the value of insulation, moving air over it. And this air, of course, will feed lots of things in the house. Here is just a wall panel. I'm air sealing on this job. So how are you going to air seal all of this? This is all connected to all of the other leaks in the house. How can you air seal this? Read my book. I'll show you how. So this is what we're doing in our buildings. This is why our buildings leak 10 to 15 air changes an hour, you know, and we cover this stuff up and you never know it. T&G, tongue and groove roofing. Oh, this guy calls me, he said, you know, when the wind's blowing, I can feel it. We're in the bedroom, this is the bedroom. He said, we can feel the air moving in the bedroom. And we put our hand up here and we can feel the air coming out of these, this tongue and groove. This tongue and groove goes right over the top plate and to the outdoors. So these are tubes, funnels, straws from the inside to the outside. Another part of the room, evidence that air could get through it. Water was blowing through it. See the water stains? So with the air came moisture and water and just blew right into the, it was in a windy location and blew into the living space, connecting the outdoors to the indoors with holes. Infrareds, these are not mine. I borrowed these from Fleur. I should give them a recognition. They said I could use them. Fluke, I mean. Here we are outside a building. This is a stunning infrared picture. It's cold outside, and this is heat. There's positive pressure in the house, and heat is leaking out through this old window installation. That's heat coming out. Positive pressure is pushing the heat inside out, and there it is shown. Here we are, negative pressure inside the house, and it's sucking attic air, cold air in the attic, into this unsealed hatch cover in the attic. This is a panel, again, sucking negative pressure in the house. Through the tubes, the conduits in the panel is sucking cold air from the outside into the house. So the 9 rules of successful air sealing. I'm gonna take a drink break. No questions out there, huh? All right. So look, all of you out there, if you just take home this next 7 minutes of lecturing about the 9 rules, that would be pretty much all you need to be successful on your next job and all your future jobs. Of course, start out, set a maximum air leakage target. That doesn't happen. You know, when somebody hands you a set of plans or you're designing something, you don't say, we want it to leak not more than 2 air changes an hour, right? So it's like driving without a map. Just do the best you can, you know, or it's not even on the plans. It's not even done. It just says, the plans might say foam seal all the holes. It's just ludicrous how primitive we are in air sealing our buildings. If you get it on the plans, it assures that the architect understands the air sealing measures, right? Architects, that's where it starts. Air sealing starts in design phase. It starts with the plans. I'll get to that. The contractor is liable to follow the proper air sealing if it's on the plans, maybe. Final outcome should be close to the target. It gives you a direction, a place to go by setting a target. Suddenly, air sealing is on the map. Access to a blower door. You can't verify or even find leaks without a blower door. This picture here, this is a job I was consulting on. I was doing building shell and air sealing. And I worked with this contractor, and he had never done air sealing before. And I said, okay, this is good. I like working with people who have never done this because they're the people that need to know it the most. This contractor had never done air sealing. So here we go through this whole retrofit. It was a really good access, a retrofit, and I worked with him. He was very, very open and interested and eager to learn. And here he is with the manometer in his hand, a blower door on the house, and he got this place to under 1 air change an hour, and he was just delighted. He just, after months and months of doing this work that was meaningless, when they actually put a blower door on, it suddenly had a meaning. Allocation important for a job. Somebody's got to sit down, the contractor, architect, homeowners, and talk about money for air sealing. Air sealing is not cheap. The deeper you go, the more it costs. You have to talk about money on the job. And that comes from the planning stage. If you plan air sealing, it's easier to talk about money. You can get an idea, a picture of, well, how long is it going to take to do that, and what do we need for there? So for architects, this is critical, totally critical. Air sealing, this is where air sealing starts on a job. Here's an architect I work with in Santa Cruz, and she had never really attempted an airtight building. She heard that I'd do that, and she hired me to work with her on the plans. So she sends me sheets of plans. I just love sheets, not PDFs. And I said, okay, I circled a typical section. This is crawl space, the floor joist, the sidewall. I circled this section, and then here's another typical section. And I said, okay, every time you get to this on the plans and the assembly, this is what we're going to do. And I drew out all of the details for how to make that transition indoors, outdoors, airtight. There it is. It's on the plans. The materials, what to do, and I could guarantee if they did this over here, it would not leak. She went on to, this is cool. She was really, this is great art. She actually devoted a part of the plans to air sealing. Section 10719B6, air sealing. It's on the plans. The type of materials, who to call, what to do, and so it's very clear. Suddenly, air sealing is going to happen on this job, right? And if it doesn't, there will be liability to pay, maybe. Inform crew, this is really important. If you're doing an airtight job, the crew has to know about it. You can't have one person on the job going around air sealing with nobody else knowing. I suggest if you're doing an airtight job, you sit down early on the job, lunchtime, gather a circle, buy everybody lunch and say, okay, we're building something a little different than what we did last year or last job. This is going to be an airtight house. And this is what it means. Make a drawing. Bring in a whiteboard and draw something on the wall and say, this is what air sealing is. And this is going to happen here. And I just want you all to know when somebody comes around and says this or that, it's about air sealing. You have to pay attention. It will suddenly bring awareness onto the job, and it will guarantee you that you get a better job. The most important is this person, the air sealing specialist. That happens to be me there. So more jobs fail because this person doesn't exist on the job. Typically, there is no air sealing designated person, and so air sealing is just handed around to different people. No one's really knowledgeable or knows what they're doing. There should be a designated air sealing specialist on the job who oversees all the trades. Plumbers don't do air sealing. Electricians don't do air sealing. Carpenters don't do air sealing. Without the supervision of the air sealing specialist, you will fail if you don't do this. Nothing will be covered up until the specialist has inspected it. And the air sealing specialist is responsible for all the holes, and then right down to the blower door tests. So if this person is there, and everybody and the crew is informed, and they know that this person's there, and that they have to pay attention, this person gets absolute respect, right? But you will fail if you don't do this, if you just kind of haphazardly pass the can around. Rule number 8, an array of air sealing materials and strategies. This is my air sealing shed, tool shed. It used to be full of skill saws and sawzalls. That's the other shed, actually. So this is comical. This is air sealing tools in 1998. Basically, that was it. Can foam, right? Still is, actually. This is air sealing tools in 2018. You need to understand and know. That's what we're going to do here in the next two sessions. You need to understand and all of the possible materials you can use to air seal a building. This is equally as important as the air sealing specialist. This is so critical. The person who's air sealing, the main air sealing person, or the person who's doing the air sealing, has to have extreme focus and, I would say, passion for mundane details. I mean, what it comes down, when you're air sealing a building, it's stupid, crazy work sometimes. I mean, you crawl 10 feet through muck and junk and horrible stuff in a crawl space just to plug 2 holes. You know, it's like, come on, give me a break. Why is that important? But the air sealing specialist knows that is important. That's his work, that's his trade, that's the rule for success. You have to do that. And you have to have somebody with this really focus on air sealing. The next big problem is, who is this person and how much do you pay them? Can you find a laborer to do this and take on this passion for air sealing? Or are you going to pay somebody to be an air sealing specialist and pay them $60 an hour throughout the job to do air sealing? If you want to be successful, you will have to pay somebody $60 an hour or whatever it takes to do the air sealing. You'll have to have an air sealing specialist if you want to be successful. Otherwise, you're going to come up with some number that might be disappointing, or you may get lucky.
Hey, Terry,
Yes.
it's just after 10 o'clock. So
All right. The
we're
perfect
gonna,
time for a break. Perfect time.
excellent. We invite everyone to take a 5-minute break and we'll regroup here at 10:10.
10:10. Thank you. So can we talk amongst ourselves without anybody else hearing?
And unfortunately, we can't.
Oh, I thought, okay. Well, I don't have anything to say.
All right. All right. It'll wait till the end.
Yeah, any questions for me though? How's it going? Any questions? And
No, everything's going smoothly. We haven't gotten any questions in the chat box just yet, but
okay, good. All right. I'll see you in 5 minutes.
all right.
Shit. Can you hear me, Ian?
I can, yeah.
Oh, yeah. I'm wearing a sweater. It's so cold here.
Same deal here.
Is it? Oh,
Yeah, it's like 60 degrees.
yeah.
I guess. Well,
Lucky us. It's probably 90 in the valley or something.
right. All right, everybody, welcome back. I hope a 5-minute break was plenty of time to maybe get a beverage or get a little more comfortable if you're cold inside. Terry, you're welcome to take it away.
Hold on a sec. I just start eating something I don't want to eat. Okay, so here's some really important stuff. The 3 absolutes, and I'm not kidding, as material. It's on the left here. So for the whatever you use for air sealing, you want it to last. Let's start out with longevity. Whatever you use, you want it to last a long time, right? Like you want plumbing or a cabinet or framing, you want it to last for a long time. Why wouldn't you want air sealing to last a long time? Given its value, how important it is in a building. So the materials will last a long time. Whatever material you use to plug a hole or seal a gap, you want it to stay stuck on there for a long time. And that's about adhesion. And flexibility, whatever material you use, when the materials move apart through earthquakes or shrinking, contraction, different kinds of movement, whenever they move, you want that material to just come back to where it was, like a rubber band. So you want adhesion, you want it to stay stuck, last a long time, and be flexible. So down here, this is a super, this material here is 8 years old. I keep it in a can, and look at the stick to it. Look how sticky it is, and look at the adhesion here. That's the ultimate air sealing material. It won't fail. And a lot of these materials that I'll be showing you have been advanced age testing for 60, 70, 80 years. Elastomers are a new generation of materials that pretty much the best air sealing materials now are based on elastomers, which are long chain polymers. It's complicated, but basically the stuff that comes out of a tree, a rubber tree, that's an elastomer. This is an elastomer. So this is the quality you want in any material. You could mix up toothpaste and bubble gum. If it has this quality and lasts for 60 years, you got the perfect air sealing material. If it doesn't, then go elsewhere. So you have to achieve this. I mean, you don't have to, that's the best achievement. Then the next, access gets the big door here, the big box. It's an essential condition because if you cannot get to the air leak, you can't seal it. Actually, there's a new gadget on the market that says it can. It does, actually does. So you need access to get to the leaks. If you can't get to the hole and plug it, then you can't leak. So you have to have access to it. I remember that early slide I said the opportunities for deep air sealing in buildings. That was all about access. All of those examples I showed you were taking off materials so you can get access to the leaks. Longevity, talked about that. You know, if you had a plumber, if a plumber said, you hired a plumber and the plumber said, yeah, well, you know, we always, our prices are really good. We usually beat, you know, all of the other prices. But, you know, the problem is after maybe 8 or 9 years, a lot of our plumbing starts to leak. Would you hire them, right? Or electrician? Yeah, they short out after a while. So why would you want to skimp on air sealing, given that its important value? The 3 miscellaneous edicts of air sealing. It's always preferable to air seal at the pressure boundary, the balloon skin, right? The primary leak, not the secondary leak. If you air seal down here at the primary leak, you stop the leak. If there was a tire around these tubes usually go in tires. If you patch the tire, it can still leak if the tube is leaking. So here is typical tape seal. We're underneath the house in the crawl space. Here's the balloon skin, the pressure boundary. This is the bottom of the subfloor. That's the designated airtight layer. Here's punctures in it, ABS, and a retrofit. They were tape sealed. Why tape? Tape to me is the high bar of air sealing. It's the most expensive. It lasts the longest. It's been accelerated, advanced decay, I forget the name of it. Accelerated aging for up to 90 years or something. It doesn't change. And tape is just very, very super good air seal material. So here is edict number 2. There only needs to be one pressure boundary. Again, here's the plywood. That's the designated airtight layer of this building. There's a puncture in it, this metal box, and it's being tape sealed around there. So after you seal this, you don't need to go to the other side of the wall and seal anything. You just need to do this once. Unless you have a lot of money, you could air seal as much as you want. But you only need one good one. This is a designated, on another job, this guy was a designated person. I talked to him, I worked with him. This was a pretty large job, and he had 4 or 5 guys working under him to tape seal this entire house. And on that house, we got that a little over 1 air change an hour. It's a pretty large house, big. Edict number 3, don't do dirt. Don't waste your time putting any air sealing material on top of dirt. Here's an attic, right? If you can't air seal this attic if you can't get to the leaks down below. So we're vacuuming out the attic to get to the leaks. So that's the 3 edicts. Air seal options for sidewall, floor. These are options. So everything I'm showing is options. You can use any combination thereof, or you can invent or find your own ways of air sealing. It's an open field, but I still stand by, you have to stick to the 3 absolutes. The materials have to be excellent. So let's go through sidewall, floors, attic, crawl space. So bottom plates, going back to the early slides, remember I showed you how the bottom plates or places where air can get in buildings. Well, here's a building, again, it's a pre-plywood building. It's a lumber sheathing floor, bottom plates set down. And this is the ability for air to leak underneath the bottom plate as the building changes and shrinks behind closed doors. You'll never see this happening, but the leaks will always come out of there. So this infrared illustrates what happens when a bottom plate leaks. So what we've got going on here, there's a blower door on this building. It's negative pressure, which means the fan's blowing air out of the house and it's trying to desperately to make up air from the outside, and it's sucking in outside air. So it sucks in outside air through the bottom plate here. That's blue, that's cold air. And I don't know if you use infrareds, but red, orange is hot and blue is cold. Green is in between. So negative pressure is desperately trying to get air from outside, and it sucks it in from the bottom plates, right in underneath the baseboard, on top of the baseboard, and out of the outlets, secondaries. These are secondary leaks. Primary leaks out here, outside the building. If you're looking for trouble in buildings, that's where you go to look for leaks. Another place, hidden place, this is a shear wall. This is my house, actually. I'm glad to say and ashamed to say I built this before I knew about air sealing. And I was cut a hole in the wall to do some work here inside the wall. And I noticed that my shear wall was not touching the mud sill, the pressure trees on it. It wasn't touching. So, again, centerfold. So air gets behind that shear that's not touching. This could have been a bump back there or uneven framing, which happens all the time. And air gets behind it and is right into the building. Here's another part of a different building, a slab, concrete slab. And this butter knife can slide behind the plywood right into the wall assembly. So can outside air, and so will outside air. Bottom plates. Here's a house being built up the street for me. Not my job. I go. I study buildings and I look the way they're going up, and I figure out ahead of time how they're going to leak. And so this was a pretty high-end, very actually high-end building. It wasn't large. It was just a few thousand square feet, 2,500 square feet, not huge, but high-end builders. So I went around and knowing bottom plates were leaks, I went around with this butter knife and I wanted to see how often I could slide the butter knife under the bottom plate from the outside to the inside. And I guessed between 5 and 10% there was gaps underneath the plate, right? And once air gets in this gap under the plate, it can come up through the plumbing hole. This is a primary leak, and it comes up secondary through here and shows up in an outlet. And it goes right under the plate and out, as illustrated here. Here's a pretty thick Lennox PVC saw slid under the bottom plate, 2x6 plate, right into the house. That also is air ability to go into the house. And this is where that air coming in there looks like this when you put a blower door on it. And in reality, here's a corner. To show you the framing is not perfect. Even though these were high-end builders, these are beautiful cuts. The cuts were gorgeous. You think they framed it with a chop saw. But this is what lumber does no matter what we do. It has gaps in it. Subfloor, not perfect. So here's our runways for air to go into a building. You put a piece of plywood over it, and you don't necessarily stop this unless you do some gasket work, which I'll show you. Here's another building. 6 months ago, I was in Oakland, California, and it was a 1 square block, multifamily units being put up and on slab. And look at this bottom plate. Now they wanted to get the wall level because the slab wasn't, obviously. So what they do, they shimmed up the bottom plate. Why they do that? Just to make the wall level. But what happens is, look at that runway for air. You put plywood over that, and it's gonna leak a lot. This bill, I would dare to say, if you put a blower door on this brand new building, changes an hour. Memphis, we're just going around the country and how we build. Here's a bottom plate of these were kind of condo multifamily units or something in Memphis. Memphis is pretty funky the way they build there. Here's a bottom plate on a slab. Now look at all of these gaps. You put plywood over this metal plate, there's no way it's going to sit flat on framing. And this gap here, massive leaks when you put plywood over this. And again, the carpenters it was not on the plans, the crew was uninformed, nothing was in place to air seal this building. And this was, I don't know, maybe 4 months ago. Stockton, California, another house. This zip system, fabulous, nice system for making buildings airtight. They used the nice airtight materials and had no clue about what airtight is. Look at this corner. Air leaks under, through. Even when they trimmed this out and everything, I didn't see it finished. Air was going to be able to get underneath and into the building easily. This is the way we're building. We just have to stop doing this. It's just criminal in a sense. We're just blowing our fossil fuel burning carbon out these holes in large quantities. So here we are back inside a house, a job I did a year and a half ago. Again, I was mostly air sealing on this consulting. Put a blower door on, and when I put the blower door on, negative pressure, I could put my hand a foot away from this outlet and feel the air coming in. That's why I call it a gusher. And then I took this pruning saw blade, pretty thick blade, and I could just slide it right outside the building. Again, that's a bottom plate leak. So here's a fix-it for bottom plates. Really simple. If you're putting down a new bottom plate, put a gasket under it. Don't ever put down a bottom plate on an exterior wall, especially without a gasket under it. Now this is a really high, it's an EDPM, high quality gasket for a 2x6 wall. These are bomb-proof gaskets. And the important thing about a gasket under a wall, it has to go edge to edge. You can't just be a little bead running down the middle. Problem for leakage, solution, simple. One gasket stops all of that. Okay, let's go to the back of the plate, right? Here's a 2x6 back of the bottom plate. And the back is Simpson, it's a strong tie, pretty thick gauge. I put numbers on here so you could read the depth. So this thing slid 9 inches behind the plate right to the outdoors. And guess what's gonna come in and out of that is air as well, right? This is the way, this is like a 50-year-old building or something. This is a building, 50 years old. This is a brand new building going up. So the way to stop that leakage, dead stop it, beyond a doubt, is you put a gasket on the outside of the building before the plywood goes on it, and air will not go up from there. A gasket under it, and air won't go up from there. There's lots of gasket choices. You know, I could show you a live thing of gaskets. I'm not sure how good you can see this. Here we go. So here's gasket choices. If you just Google sill plate gaskets, this is thicker stuff. Thick is important. You don't want an 1/8 inch thin gasket under your bottom plate, particularly on a concrete slab. You want at least a 3/16 or a 1/4 inch gasket underneath your bottom plates on slabs. On interior walls, you may be able to get away with less because there's less movement. But if you just Google sill plate gaskets, here's the one that was in that photograph. I have references for the names for all of these products at the end of the show.
Terry, we have a couple questions about the gasket. We have one about how the gasket adheres to the concrete.
Good question. I have no idea. No, I'm okay. Any way you want. You could use a, you have to make sure it's compatible. You could use an elastomer. Most elastomerics are compatible with anything, but you could just simply put down a bead of, a squiggle line bead of elastomeric adhesive. That'll be fine. And it would not react with the EDPM or any gasket material for that matter. If you're putting down an adhesive under the gasket, make sure, I would stay away from petroleum stuff because they may have a tendency to deteriorate the gasket material itself. So stick to elastomeric adhesives. In wood, it's obviously easy. You can just staple it down if you wanted to. I hope that answers it. Yeah.
There's been another question about if is the gasket made of some type of rubber?
Yes and no. This stuff here, I think it's EDPM. I forget what that stands for. This is it is a rubber. This is very high-end, expensive gas material. These other ones are foam, petroleum foams, right? And but if it's rubber, you're paying a lot of money, but you're getting a lifetime gasket. And I would say if you're going under a slab, I would have a tendency to use a better gasket. Here's products that are made for sill plate gaskets. Some of them even have self-adhesive, right? It's sticky. But again, Google sill plate gaskets and pick out what you need for your particular situation. Okay. So here is another option for air sealing. If you don't have access, remember it's all about access. This was a stucco building that was leaking a lot, and the stucco was going to remain on. The interior was being half gutted and remodeled. So I told the contractor, I know that the stucco had massive leakage. See this picture right here? This was that same house. Between the 30-pound and the bottom plate, there was huge gaps going right outside. So knowing that was there, I told the contractor, I said, go around and make a 12-inch cut all around the perimeter walls to the outside on the environmental walls, and I will come in and air seal it, and then you can drywall it back. Extra expense. That's not cheap, right? But it made the difference between this building leaking 11 air changes an hour and 3.5 when we got finished, right? So this is actually a product that I invented and made, and it's elastomeric basically with the granules in it, and it can be sprayed or brushed on. And you can see I flooded this gap back here, and then I flooded the gap under the plate there, right, all around. So then that pretty much made it not totally airtight, but very airtight. It's an expense, but if you're trying to get your building, a lot of these zero net energy buildings, they are requiring 2 air changes an hour. If you're doing retrofit job and you start out leaking 7 or 10 air changes an hour, and this is where your air leaks are coming from, that's what you're going to have to do. That's what we're going to have to learn how to do to air seal the building. If there's money, it's always about money. Remember the slide? Money. Talk about money. The money's got to be there for it. You have to talk about how much it's going to cost. And the homeowner just might say, you know what? I'm not willing to spend $3,000 air sealing the bottom plates. So it's over. So you do the best you can. Oh, so here's some sill gaskets. This was some underneath. This was, I don't know the name of stuff. That's what I showed you here. But again, you can Google sill plate gaskets. Here's another one by self-adhesive bottom for sill plates. This was my first air seal attempt job on a house. This house actually got, I'm sorry, this is my second attempt to air seal a building. And it was supposed to be a passive building. And we tested it out at like 0.3 air changes an hour. Really incredibly airtight. But I didn't know much about sill plate gaskets. What I did was I got 5 gallons of Henry fibered roof tar and I smeared it on the top of the slab, and I set my plate in that, wet set it in petroleum. So that was a capillary break and gasket material. There's no really rules. The rule is air seal it, and then materials they just have to last. And after that, just do whatever you want. So here's other options for slabs and air leaking behind. This is a plywood wall down here. Here's a plywood. This is the house that I showed that contractor, and we got it. I forget. It was pretty airtight. He was blown away by how tight it was. So we know that it's going to leak behind the plywood of this old slab. So there's tapes you can get. This is called Hanno Dewies. This is German tape. There's tapes you can get that will stick to plywood and concrete. Total, easily. Here's another tape, plywood to concrete. Here's let's see if you can see this. So this is a sample I made. This is a penetration in concrete using tape to seal around it, right? This could be a wood to concrete, but there's tapes that will stick to concrete. Now look at this. So here's the problem. Air gets behind it and up. You tape this, and this. You continue the balloon skin. Air will not get there for the life of the tape. This tape is 90-year rated. Life of the tape. Air will not get in. It's over. The bottom plate won't leak in the bottom or the back. Plan ahead. If you're doing slabs, this is a way to air seal the entire building. Here's another way to do it. If you have no access to the bottom plate in a slab, inside or outside, I don't know if you remember, but that butter knife would slide underneath in that same building. You could just get a can of foam, and with this straw, you can stick it up into that groove there, and then light it up, and then fill it up. Here's all the excess coming out, and then you just trim it off. You have stopped pretty much all of the leakage from coming into the bottom plate. That's a very cheap, fast, effective way. You can walk up to any old building and go around with this and reduce a lot of air leaking. If you're not into can foam and gaseous foam, you can do the same thing with backer rod. I've done this in buildings. I get a lot of clients who don't, they say, what do you have that's not toxic, that's no VOC? And I give them the options, and I give them the cost, and they decide. So this job, they didn't want to use any foam on the building, and there was no access to the outside of the building or the inside. So the bottom was just stuffed with backer rod. It's an option. It's the same effect as this, but it's using pre-made toxic foam. Okay, so now, because I'm giving you some information before this is going to be a quiz, a question, and I'll give us a few minutes to answer this. This is a bottom plate, an interior plate of a wall in a house with a crawl space underneath it. Why is this not? Now this is the best. This guy bought the best. These are German tapes, the best air sealing material you could possibly buy. And he did this fabulous job of air sealing all these punctures. But why is this not a good job? I'm going to just give it a 1 minute break, and I'll come back for some answers, okay? And just write back and tell me why it's not good air sealing, okay? I'm going to take a tea break.
Feel free to leave your answers in the chat box.
So I'm not going to see the chat box, Ian?
You're welcome to. You just have to navigate to the options bar on the bottom and open it.
Okay. Yeah, I do want to see them. Not giving me an options bar. Oh, the options bar is on the top. There's no option bar at the bottom. Polling participants. No, I'm not getting an option.
You may not be able to see the chat box when you're sharing your screen. I think I
Yeah,
had the same issue. But we're getting a few answers. The seal
good.
plate is not sealed. Seal the plate. The seal is not complete.
Wait, stop. Say that again.
The seal
You're too
plate.
fast. Say that again.
Sealed.
I think I know what that means, but I'm not sure. It's not sealed. You mean there's no gasket under it?
Well, the answer just reads that the sill plate is not sealed. And there's another answer that the seal is not completely around one of the pipes.
Okay. Well, that one is not correct. The second one. The sill plate might be correct. But what I'll tell you is that, remember, when I showed you the pictures of how bottom plates leak air, they leak air not only from the holes in the top, but they leak air from the bottom. So imagine air comes up through the crawl space and it gets to these holes. It can't get out the holes. That's done perfectly, right? But it can get out from underneath the bottom plate. The simple way to air seal this, much, much simpler, would have been to go in the crawl space and then air seal, put this tape on the punctures right at the pressure boundary. This is the balloon skin. This is the pressure boundary, right? The subfloor, the designated. This top plate is not the pressure boundary, right? So if you go underneath and you air seal each one of these punctures at the pressure boundary, it would be airtight. It would be a quicker, simpler job too. That's the answer. So here, this illustrates why this won't work, because air can get underneath the bottom plate, right? You can seal these, but air can still get out of there. This is training. This is so when you go to air seal buildings and you look for leaks, this is training so you'll know where that leak is coming from. The secondary, the primary, the source leaks. Once you know that, you'll know how to air seal. So here we go. This is this is a good illustration for tape sealing wood to concrete. This was a pretty large, fabulous job in Cupertino. This was a Google guy. This is an amazing house. Anyway, he hired me solely to do the air sealing, to work with the crew and blah, blah, blah. And so I came in and did that. And I came up with a strategy for air sealing and the materials and got it on the plans and worked with the workers, and we were pretty successful. But this it had a full basement, concrete basement. So the basement is now part of the conditioned space, the pressure boundary. So the concrete surface of the concrete is the balloon skin, and the balloon skin has to be continuous with the plywood is broken here by a air gap. No problem, tape seal it. These tapes will seal concrete to the plywood. All of the seams, the gaps of the plywood were taped. So again, visually, we're making this whole surface here, the balloon skin, and we're with tape. On this sidewall here too, here's another opening where the plywood, wherever plywood terminates, that's where it can leak. So these edge terminations are tape sealed. Here's another, this is really gaining popularity, a lot of ground in air sealing. It's kind of a cool concept. It's made by Henry's Blueskin. Basically, it's like big rolls of very expensive sticky tape, and you roll it out, and it has not a highly sticky surface, but sticky enough it'll stick onto plywood. You could take it off, and you just wrap the whole building with it, and the material itself is airtight. And then when you put seam to seam, it's airtight. The problem is, again, if there's not an air sealing, what they did wrong here was they did this beautiful membrane, airtight membrane. They were weak around the windows. This should have been taped, super taped to the blueskin. And then down here was not taped at all, so air could get behind there and into the building again, right? Another problem with this, the blueskin's cool because you could be building in the rain, and on a sunny day, you could wrap the whole building, and it's waterproof. That's a real benefit, right? Especially building in rainy climates. The problem I don't like with this, it has a really low perm rating, which means it doesn't breathe very well. 0.3 perm rating is very weak. It means it basically is a vapor stopper. Vapor can't pass through the wall, which can be an advantage, but in our climates out here, we want our buildings to breathe in either direction, pretty much. Here's more choices for air sealing the exterior. Liquid, this company Persoco seems to be gaining a lot of ground. They're really cool people. They make these liquids. This is I call this liquid tape. You brush it on around the terminations of the plywood, and there's your balloon skin airtight layer around the opening. And then the seams are brushed or rolled airtight layers. And this could be tape, but they use liquid. And then it's top coated with another airtight material. This is the whole house wrapped, sealed with liquid around the windows and the joints, and then top called Cat 5, which is a weatherproofing and an airtight layer. It can be brushed, rolled, or sprayed on. And this stuff has a perm rating, 18 perms. We won't get into perms, but you really have to pay attention to perm ratings of materials when you're doing assemblies. I mean, why not? Sometimes you could kill a wall by having the wrong perm rating in it. That material zip system, real popular, gaining popular, particularly back east. So this, not my crew, not my company, not my job. Next door to my mother's house, they put up this house, this addition, and beautiful pieces of plywood. It's got weather shield on it, and they tape sealed everything, right? There, you can see it. That's a tight job. There's your balloon skin all around the house, right? However, because it was an uninformed crew, they didn't have a designated S, they just followed directions out of the box. They forgot to tape seal the bottom of this to the slab. So all of that work, and air is still going to come up behind the slab. All that we had to do to fix this would be to tape seal the this wood to the concrete slab like this. But it's about, so here's a part of the building, same system with the tape on it, but here's a slab, air going to get behind it. Tape along here would have just killed that. Instead, they just cover it with siding, and you can't see the leak, but it's there. So this is more about you got to watch your workers. Don't assume that you buy a product that's going to be installed right. You all know that about, and you have to watch the installers. This cannot be air sealed. This 90-year-old building. This was a job I had. Actually, I took this job on, and we wound up getting this place just under 1 air change an hour. That was my first air sealing attempt actually at a building. It's a long story. This is about no access to the exterior. This was a stucco building. The stucco was going to stay on, and it was stucco and then 30-pound paper and then these solid boards, this lumber sheathing it's called, board with gaps in it. So no good insulator would insulate a wall that could leak water into the cavities. So I had this idea to do it from the inside out. So I went inside and I took a foam gun. I foam gunned all of the big gaps. It was like 1/4 inch, 1/2 inch gaps in all these boards. And then I sprayed elastomeric over the top of it. The elastomeric became an airtight layer. It's vapor open. It had a perm rating of 17. It could breathe in and out. It was watertight and airtight. And then you could insulate this cavity. So it was kind of like working from the inside out. Here it is sprayed and the blocks going out. And here's the bottom plate on the slab, on the concrete wall, sprayed with elastomeric. It could be brushed on, rolled on. Roof. So here's roof choices. This roof is tape sealed, and including the rafters sticking out. See these rafters sticking out? They were tape sealed as well. That's pretty expensive work. Like these eventually would get tape sealed around there, because these rafters fed directly into an insulated cavity. If these rafters fed into an attic, that tape sealing wouldn't be quite as necessary. But feeding into an insulated cavity, it's essential. Note, there's a big difference. If you have an insulated, enclosed, unvented cavity, it should be airtight on both sides. Both sides. Here's a retrofit flat roof, flattish. It's like a 3 and 12. So the roof came off. This roof was going to get solar panels eventually, and so it needed a new roof. The roof came off. I pulled the plywood off. I'm sorry, no, I didn't. This is the original plywood, and when I was looking at the old plywood, it had tons of holes in it, nail holes. So I had to these holes connect. I don't want to vent the insulation. So I plugged all the nail holes, tape sealed all the edges of the plywood, and then tape sealed or caulk sealed the edges of the 2x2. So this entire thing would get filled in with 2-inch polyiso foam and add additional insulation onto this old roof. And this would become an airtight layer as well. This is showing this is really nerdy, turdy air sealing stuff, but this plywood seam right here goes under the 2x2 and out of the building, right? If air can come underneath the plywood and get out of the building underneath the tape. So I would drill the hole in every one of the plywood seams going out and plugged it so air couldn't exit the building. That's what this is about. If we have time, I'll get to show you more what that looks like. So here's rafter tails coming out of a building. These joints here need to be sealed. This is a high quality, this is called Air Dam by Persoco. I really like this stuff, but there's lots of good elastomerics. So this is air sealed with a caulking gun and a fingertip smeared, and then the seams are tape sealed on the plywood. So it's a combination of tape sealing and caulk sealing. Fabric sealing, not done too much. I'm not crazy about fabric sealing. Passive House uses a lot of fabric sealing. Europe uses a lot of fabric sealing. This job, I was, again, air sealing consulting, planning, and the architect, he wanted to use, it was about set. He actually, a lot of this was about salesman. The salesman guy he was friends with sold him all of this stuff to air seal with. And I wouldn't have done this, but the salesman said, wanted to sell his stuff and said, buy my stuff and do it this way. So here it is, fabric sealing in the ceiling. The fabric is tape sealed, there's furring strips over it. The plywood, the drywall gets hung on the furring strips. And here the knee wall of the attic is fabric sealed, same here. So fabric can be a versatile way to air seal. You can mix fabric sealing. This building had fabric sealing, drywall sealing, plywood sealing. It had 4 different air sealing methodologies. But this is just to give you an idea. If you hear about fabric air sealing, this can be what it looks like. And notice here's a hole in the fabric. It's got to be tape sealed around the hole. And all the seams of the fabric have to be tape sealed to make it a balloon skin. Gasket sealing. So sit up in seats, take note. This is the first house that I air sealed to under, let's say 1 air change an hour. I used a lot of gasket sealing, and I didn't know what I was doing. It just seemed like a good idea at the time, but it turns out it works really well. And since then, I've been employing it as a lot of strategies for air sealing. And the reason, so this is what gasket sealing is. Here's a car door, right? The reason that you can drive in a thunderstorm at 60 miles an hour and have no water or wind come in, why is that? Because this door has a continuous, unbroken, thick, bomb-proof killer gasket all around the door, right? You know how good these are EDPM gaskets, the same one as that one I showed you in the house. So I thought, well, if it works for car doors, it'll work around a window, it'll work around a wall, it'll work around anything, right? What this drawing illustrates, these green lines in this frame building are places you could put gaskets. And if you put sheets over them, there'd be more, of course, with sheets, and then air can't get into the building. You're kind of done, right? It's really done. Like on this door needs no other air sealing except that one gasket around, of course, the window, and it has its own quasi gasket system. So here's gasket sealing in action. Here's a frame building. Here's a subfloor. Here's the funky framing that's never perfect. Subfloor is never perfect. If you put a gasket across this, that's where it's going to leak. That's where the air is going to come in when you put plywood over it. You put a gasket on that. Here it is down here, that, and then you put plywood over it. Again, air can't get into the bottom of the building. Over here, there is no gasket. That's a pretty sizable gap there. Hasn't been done yet. Here is a close-up of the gasket. Now, see this gap under here? Air can leak under there. That's the crawl space. That's the crawl space. You might say, hey, you forgot to do that. But, it's going to leak in the crawl space. Not the end of the world. It's outside air anyway. But the important thing to gasket seal is that. Here, again, is that high-performance EDPM gasket. Look at the compression. This is a 2x6 sitting on top of I can't think of the name of this gasket. It's in the reference. Here's the bottom plate sitting on top. Look at the compression and the sealing. It has bulbous edges and it seals particularly well with the edges. But that's gasket sealing illustration. Here's interior drywall gasket sealing. If your drywall is becoming part of your airtight layer, there's this stuff, Dow drywall gasket, comes in a can, looks like gun foam, but it comes out in this really weird, it's kind of foamy, it looks like shaving cream almost. And you put it on a top plate and it sets up in a few minutes, and then you set your drywall on there and air can't get behind the drywall into the attic. Again, you can look it up, Dow drywall gasket. It looks just like a foam gun, but it's water soluble, and you actually clean out the gun with a hose, with a water hose. Here's more exterior gasket sealing. This company, Denarco, I like them. It comes in big 60-foot rolls of any width you want. So here is a door opening of a house with Denarco gaskets, just like the door opening on a car. Air can't leak behind it. Floors. Let's go through floors. Balloon skin on top of floors. It's tape sealed. This is an old funky, this house was late 60s or something. The plywood was very leaky for different reasons, particularly along the gaps and edges. It was T&G. So this tape on the top of the floor simulates this entire floor being one continuous skin. It's an option. Here's, suddenly we're back to gaskets. Sorry about that. Oh no, this is tape and gaskets. So, so here's the opening in the floor, right? The floor is fabric sealed, really not my favorite thing to do. And then the fabric is taped to the opening, and then the opening is taped, and then the opening gets a gasket around it. So when the hatch cover goes on, it's tight. So this opening right here, that's an access door into an attic from inside a house. It has no gasket around it, right? And it's cold out, negative pressure. The blower door is sucking air from outside in, and it's leaking handily the holes around and the gaps around the hatch cover, the access door, because there's no gasket around it, right? This was one I recently did. Same hatch cover. I would take the access door and put a gasket around the whole thing, and then build up some foam and drop it on top of the opening, thus getting R value and a gasket seal around it. And the weight of this assembly would hold it tight on the gasket. Here's a hole in the floor, same concept, upside down. And notice this hole here is tape sealed all around it. Sheet metal, hole in anywhere, drywall, whatever it is. These tapes, I like this stuff, Siga Wiglove. I call them super tapes. They're just amazing. The adhesion is just unbelievable. And the flex is incredible. And the longevity is amazing. So this is a whole, look at the gaps, tape sealed. The sheet metal guys, HVAC people, they come in and they do, they always of course always tape seal the ducts coming into the room, and they use metal tapes, which can be pretty good, but there's some situations where metal tapes just don't quite, like in this one. You may need something a little more flexible and than metal tapes around here. So I just, whenever I can, I use these Superflex tapes that'll handle any conditions. So this is a retro job again, kitchen remodel. And I came in and his holes in the floor, right? This is an island sink cabinet, just the cabinet in the middle of the kitchen. And the plumber, of course, and the electrician drilled holes in the airtight layer, the floor. And of course, we know these are going to leak. Usually, if it was air sealed, and it probably would be, somebody would come along with some gun foam and spray these things, which would be better than nothing. But I don't use gun foam. I don't use gun foam for air sealing, by the way. And I'll show you why not. So I came along with tape because it's the best job, and there was money on the job, and I tape sealed all of these openings. Now I know my tape sealing I did an 80-year tape sealing job here, and these island sink cabinets, these ABS pieces move a lot, huge amount of movement, which could easily break a foam connection, as do the wires. It took me 15 minutes to tape seal these for an 80-year job. I'm pretty fast at tape sealing, so it might take you half an hour the first time, but you'll get better at it. And then you walk away knowing you just did the best job of air sealing you do. So here's why, this is why I don't use foam for air sealing. Another job, this is a commercial job, some offices I did, and the electrician came along and he said, I finished the electrical boxes and I air sealed them. And I said, oh, really? Okay, thanks. So I went back and looked at his air sealing. It was nice of him to think of it. Really nice of him to think of that. So here's his foam air sealing that I looked at. And if you look closely, you can see the foam doesn't quite touch everywhere, and there's gaps, Foam gives you the illusion that you have done air sealing. That's one of the big problems with foam. It gives you the illusion that you have done air sealing. But remember the mundane focus to details? A focused person will look at this and go, yeah, that's pretty much, that foam took care of most of it, but it didn't take care of all of it, And why do a half-assed job? Why do an almost good job? maybe because there's no money and it's fast. That's a good reason. But if you want to do a better job, this is simple. So I took this almost good job and I just took elastomeric caulk and I went all around and caulked it in there. And then I took a stick on my finger and I smeared the elastomeric, the really, really good, sticky, super adhesive, long-lasting air sealant on top of the foam. Now I have an air sealant that I can walk away from and know it's going to last for 60 years. The elastomeric is the air sealant. The foam is the gap filler. I use foam to fill gaps. I use elastomeric caulking to air seal.
There is.
Yes.
Is now a good time for a quick break?
Yep. All right. What time we're going to resume?
We'll regroup at 11:05.
Okay.
All right.
See you soon. Bye. Oh, sorry. Oh,
Hey, welcome back.
yeah, I lost everything. I gotta, sorry. Um, hmm, I kind of lost the screen here. Just give me a second to,
Okay. Yeah, I think you just need to reshare your screen.
yeah, I can't get out of this. Oh, there we go. Wait a minute. Having technical difficulties here. Yeah, I lost the Zoom thing. Well, there you go. Okay. Now I got you. So, all right. Okay. We're good again?
Yep.
And let me change the view. All right. Okay. So welcome back. Let's see. It was a good breaking point. So I'm just going to go over quickly lumber sheathing. This is completely about retrofit work. Plywood, plywood was like invented in the 40s basically, and it didn't really start making headway into the residential building until 50. I think maybe the late 30s it was invented. Anyway, it didn't start getting into residential building till the 50s. And I've worked on houses that were built in the 60s that still use this lumber sheathing. And basically, before plywood, they just used boards to fill up huge spaces. And they were solid wood and they had gaps in them. So you can almost date a building by seeing the sheathing that was. They used this on roofs, roofing, sheathing, floors, and sidewalls. So this building was actually 60s. It wasn't that old. So this is the problem, though. The other side of this lumber sheathing is crawl space, and air can freely, wildly come up through these gaps. And so, how do you air seal? How can you possibly air seal the inside of a building if they have these? You know, you could put wall-to-wall carpet on or laminate flooring. That would do a lot of it, but you have to know how this stuff is going to leak to really make it bomb-proof, airtight. So look, this lumber sheathing, the problem with this lumber sheathing, one of the big problems is when it runs out of the building. So what this bottom right illustrates is here's floor, we're outside the building, here's a floor joist, here's some lumber sheathing going across with gaps in it. And lumber sheathing boards can be funky, and air can run up from the crawl space right out of the building, or from the building, from inside the house out of the building through all of these gaps. It's just you cannot rely on lumber sheathing as air seal. So here's some methodologies. Here we are outside the building on a retrofit. Here's the lumber sheathing coming out, and there's the gaps between the lumber sheathing. Here's the bottom plate. Here's the studs up here. So here's these gaps. The air is going to freely roam in and out of that, in and out of the assembly. Here's a close-up of that, a particularly bad area. This bottom plate sits on top of the subfloor, and there's like a 1/4 inch gap between the bottom plate and the subfloor. And the next plate, you put plywood over that, massive leaks, right? Again, go back to gasket sealing. So in this job, this company Denarco, you could call them up and say, I want 160 feet of 2.5-inch gasket material, and they'll send you 2.5. That's what we did here. I think there's 2-inch or 2.25. So we just put a gasket between all this junk here, and then when plywood went over it, the subfloor would stop leaking. So here's some other ways to air seal subfloors. So here's a subfloor with the lumber sheathing and the gaps, going under the plate. Now these holes are going to go right outside the building and behind the plate. So you just take the floor, you take this floor, and you do wall-to-wall plywood on the floors. This is 1/4" plywood, and this plywood is taped to the bottom plate. Suddenly the balloon skin is now, this top bottom plate becomes worthy of air sealing, because we have moved the air sealing layer from underneath to on top. See what it looks like more. Here's the job. So here's the room with the board sheathing, wall-to-wall plywood. This was 1/2" plywood, tape sealed to the top plate. So here's the balloon skin happening now, right? Air can't get nowhere to go here. It hits that plate, nowhere to go there. It can still get up from underneath the crawl space and go out through these holes, right? So therefore these holes are sealed. The top of the holes now become worthy of air sealing and essential for air sealing on this assembly. Here on the upper left, this wall is caulk sealed, all of the punctures coming up. So we have now taken all of that funky, unsealable board sheathing and moved the balloon skin up to the top and eliminated all of that. Here's another option for funky floors that you can't air seal from on top. You can go underneath, if depending how clean and clear it is under there, you can just put this job. We put OSB on the bottom, wall-to-wall OSB on the underside. This is the balloon skin now on the underside, and tape sealed it, and air can no longer get from the crawl space up in there. Where can air get in this crawl space up into there were punctures in this, which of course we tape sealed. Another option from underneath, you can air seal it using sheet foam, right? Sheet foam taped. Sheet foam is airtight, taped all the seams. Here's a puncture, tape sealed. The sheet foam is tape sealed against the wood. Where can air come up through here? Nowhere. So here's underside of the floor, tape sealing, of course my favorite. But I don't always use tape seal. It depends on the money, depends on the time. So these are punctures in the underside of the floor. The pressure boundary, big holes. This applies to big holes anywhere, top, bottom side of the building. This happens to be a big hole in an attic, which is very, very common. So here's one of those bathtub holes I was illustrated earlier. So step one, you take some 1/2". This is polyisocyanate sheet foam, 1/2", and rough cut it, the edges to fit this more or less, doesn't have to be tight. And then you slide this foam up into this hole more or less, and here it is fit more or less into the opening. And then you tape seal all around the edges, right? So these holes don't have to be tight because the tape is going to cover any overgapping. The tape will just easily cover that. So you have now taken a bathtub hole and air sealed it pretty easily, not too much work. Here's another large hole for a shower pan. Same deal, foam. Take a piece of foam, knock a hole in it the size of the pipe, cut it in half, the foam, and then put it back to the pipe, tape seal all around it. Attic is an asbestos pipe running. This is a weird pipe. I don't know what it was. Some kind of asbestos vent running up through the attic. This is like 4 inches wide or something. And here's a big hole. Again, take some sheet foam, rough cut it to fit in this hole. Again, it doesn't have to fit tight. And then elastomeric caulking was put all around the big gaps. You could use foam gun. You could use foam gun for all of this. And then it was flooded on the top with elastomeric to make sure you could visibly see. What I like about elastomeric sealing is you can visibly see the stuff sealing. You can't see it. With foam, you cannot see the air sealing happening. It just looks like it's happening. And it might be, but you don't know. But with this, you know. You can see the balloon skin all around the opening. Here's a big hole in the attic. Sheet metal was cut, custom. Brought to the sheet metal shop. It was cut to that diameter. It was cut in half, the sheet metal, and then sandwiched around the opening, sealed, and then fire caulked around the edges. Have to use fire caulk. You know, we are rushed. I mean, we could spend this class or session could probably easily be 2 days, you know, 2 6-hour days. So it's like with everything, you know, it's things that can get a lot more complicated and there's a lot more questions arise as you work than we have time for today. Windows and doors. So just for new windows, if you're going to get new windows, here's the bottom here. Windows should have, good windows always have an air leakage number at the bottom, right? This company, Alpen, they're in Canada, I believe. Alpen makes really tight windows, super tight windows, and they leak 0. That's quite a claim, but they're tested. I think they test them at like 75 pascals. Here's a window that is made, this is a Milgard, you know, really popular window in the US. They won't even rate their windows. They could care less. Here is another window called the world's best window company, and it leaks at 3 air changes an hour. So 0 to none to 3. So look at the windows. If you're putting in windows, why not put in an airtight window or airtight-ish? This is typically what windows leak. Sliders can leak 0.4 CF cubic feet per minute as a test number. You may need to know about, I don't care about the test. This is the number you're looking for. You want these lower, right? Casement windows, I don't think that's real accurate. You can get casement windows, well, like these that don't leak any. But typically casement windows leak less than sliders. Sliders leak the most. So here's classic French doors, right? How many French doors? Sorry. So red, French doors are massive leakers. And they leak, the red arrows show where they're going to leak the most, right? And the yellow shows where they might leak. And then the big leaks are the orange ones. So this is where I've never seen a French door that doesn't do this to some degree. French doors are really gas guzzlers, massive leaks. The problems, if we have time, I can go into showing you how to air seal, retrofit air seal to make these doors not airtight, but better, almost airtight. So again, this is planning ahead. If you're doing retrofit or new construction, get a gasket that is an airtight gasket. If you put a door and you put a sweep at the bottom, that sweep is going to leak. And over time, it's really going to leak because they do. But if you use these Pemco, one of the biggest, I don't know what they call, biggest extruded aluminum company in the US, make these gaskets that have bumper stops, bulb seal bumper stop. You close the door into this bumper, into this gasket, and it's airtight. You close the door into this broom at the bottom. Some of these brooms are felt, and it's going to leak, right? This is a bomb-proof leak. So in new construction, try and design your doors that close into a gasket. If they swing out or in, you have to put an additional drip edge on top, right? Because the door is going to keep the weather out from coming inside here. But anyway, it's a design detail that you have to overcome. If you want to have a tight door, you have to have a better gasket at the bottom because that's where they leak. Make your own gaskets. This company, I've been using these guys for years. Ultrafab, where are they? In Farmington, New York. Just buy, this is a 250-foot roll of bulb seal gasket. What is a bulb seal gasket? It's this stuff here. It's basically extruded. It can be silicone or EDPM or different kinds of poly plastic, extruded plastic. But basically the profile of it looks like this. It's a round thing or square thing on top. It's got these fins that poke into a saw kerf, and then you got this bolt sticking out. So this is a 90-year-old window job. I did this job, and the owner was really old school. There was 12 old-fashioned casement windows that swung out that were 90 years old. It was so old, some of the glass in the windows was like wavy. You know, it was that old. The glass had time to sag over 80 years, original glass. Anyway, we took these casement windows, and I made a saw curve down the rabbet cut of the casement, slipped the bulb in, and here it is over here that the bulb slipped in. And then I put the gasket sticking along the bottom of the window. Here's the bulb sticking out. And so when the other casement hits this, it bulb sealed there and there. Not totally airtight, but very airtight, like 98% more airtight than what it was. Making your own gaskets. Here's the same window closed. These old windows, here's the windows installed. And another important thing is with a single latch, if you try and use a single latch on a window, it's going to leak. So I added a latch on top and bottom to pull the windows into the gasket, right? And here on this one here is, you can see the seal of the gasket on top. It came out pretty tight. The blow door numbers changed a lot just doing these windows alone. I got lower. Here is my house. Here's a retrofit door. I put this gasket sticking here. The bulb seal is there. Pretty simple. I even put a bulb seal at the bottom, and these doors got pretty tight. The key thing for any gasket around any door or any material or any window is it has to be continuous. As soon as there's a break in the gasket, that's where they're going to leak. That's why doors typically leak at the bottom, because there's one kind of gasket here and another one there, and that's where they leak. Right? So this door I re-gasketed it so that it had a continuous gasket on the bottom and the sides. This one I couldn't do that, so I gasketed his gasket sticking, has a gasket here, and it has an outside external gasket here. Not 100%, but pretty airtight. That's an old door. Here is another door with the doorknob up there and the gasket applied. Attics. So we're getting out of doors now. Now we'll go up into attics. Again, golden opportunity for air sealing is when you're doing that. If you're ever going to redo a roof, please borrow the money from your uncle and break into the attic, re-insulate it. Your attic, if your house is more than 10 years old or so, it is under insulated. So re-insulate it, take out the insulation, air seal it, and then put it back, because that opportunity will come up for a long time. And when you're doing a roof, the access to doing this work is so much easier than trying to recondition an attic from the closet access door inside somebody's house. That's a nightmare. And this is more ventilated, more light, easy access, faster, cheaper air sealing and insulation. So when you redo a roof, please borrow some money. Easy for me to say, right? This is I redid my roof and I changed my access door to outside. Valuable thing to do. Access doors inside houses are really stupid things. I mean, to have an access door into an attic in the hallway or closet is really dumb. I mean, you have to go through the house to get into the attic. And how do you redo? If you have a door outside, for the life of the building, you go in and out of the attic without disturbing the occupants. All right. Remember I said bottom plates are notorious leakers? Well, so are top plates. So this is, I'm going to skip this. I have a feeling I'll run it. We may run out of time. So these are two different attics, ranch houses. Let's say they're both 2,000 square feet. And I measured the top plates where air will leak up into the attic. The top plates, both sides, the total linear feet of top plates in both attics. One was 650, one was 820. The amount of wire holes in both were close. The amount of round pipe holes were close. The amount of round boxes cut into the drywall were pretty close. Rectangular boxes varied. Those are square holes cut in the drywall. And they both had a masonry fireplace. One had 4 ducts cut into the ceiling, and one had 2 ducts. So It's kind of typical, very typical. But everything, I'm gonna get a crayon here. This is a good time for crayon. Hold on. Yeah, it's a good time for crayon. So everything here and here will leak. There are holes that will leak from the inside of the house to the outside, mostly up into the attic. These have to be air sealed. If they don't, then there's your 5 air changes per hour. This number here, the top plates, varies how much they leak. They may leak, they may not, but if you want to make a house super airtight, you got to deal with these numbers as well. So these you absolutely have to seal. And I'll show you air sealing the what this means to air seal the top plates. So here is the we're in an attic. Here's the top plate over here, right? And here's the drywall. This butter knife here slides down the wall assembly between the drywall lid and the drywall sidewall into the wall cavity, right? The insulation. This is going down into insulation. And below that is, outlets and whatever. So there's a whole wall assembly below this. So this is the ability, once air gets in the wall, it's going to come right up through here. It's gonna, right? This is definitely a leak, right? In and out. The same way a hole is. If you drill a hole into the wall cavity, that's definitely going to leak, right? That's going to leak. So these leaks are no different. They're just more hidden and they're more variable. Sometimes they're tight and sometimes they're not. So if you want to air seal an attic, you don't only deal with the visible holes, all these holes. You have to deal with all of this lineal feet, which I mentioned, of potential leaks. That's what this 600 lineal feet is. It's the ability for air to leak here. Here's how you can do it. If you had a gasket below, you wouldn't need to do this. So here is the sandwich. I call them, it's just like a wall sandwich of a partition wall, and air can and will leak along here. So I fill these gaps with foam. If you miss this, just remember, I do not use foam as an air sealant unless I'm desperate. I use foam to fill gaps, and I use elastomeric as an air sealant because I know this stuff is adherent and lasts forever. So you got to go along all of that 600 lineal feet of top plates here and hit all of the seams, right? You got to hit all of this stuff here if you want to make sure it's really airtight. It's a lot of work, a lot of work. It's very expensive. It might be cost prohibitive. If drywall was put up and it had one gasket along the top here, right? If it had that gasket there, you wouldn't need to do this. If that gasket was there, you wouldn't need to do any of this. So when we build, please put a gasket on top. If this is the airtight layer inside, by the way. Whoops, here is that. Oh, here's that stuff I was saying. Great stuff gasket. That stuff in a can. You spray it and it sets up in a few minutes, and then you can put a drywall bed in there. I'm not too crazy about it. It's not a very durable gasket. Like this stuff here, this is like bolt and suspenders, belt and suspenders gasket. This stuff is a little weak and flimsy, but it's good. It's fast and cheap. So here we are back up in an attic. And I'm using brush-on elastomeric spray with some granules in it. And I'm brushing here's the top plate. I think this is a video. Yeah, it is a video, but it's not moving. Anyway, this is a video. But brushing all of these potential leaks here on both sides. And also while I'm at it, brushing a hole for a bunch of wires. Here's using brush on around a plastic box. Now again, if you use foam, you can't see if it's sealing or not. But look at this. You can see you can see the seal. Okay, I gotta get my, hang on. All right. Oh, there it is live. No, it's not working. Oh, that didn't work. Oh, there we go. That's pretty easy, right? Non-toxic, no VOC, non-toxic stuff. Here is multiple wires along that top plate, blasted with elastomeric using a texture gun. Here again is access. If you have access to the top of a roof, if you're taking a roof off for any reason, re-insulating, all these top plates, that's an easy time to air seal them. This is brushed on elastomeric sealing, all of that. This is top plates on a retrofit, spraying the top plates for leakage. Oh, there's a brush. Pretty easy, right? Oh, wow, that's even, I didn't know that one was live. So that's spraying the top plates. Notice the foam fills the gaps, but the elastomeric covers it. Okay, so this is a good illustration. Remember, let's go back to the stack effect. Remember I said it's really, if you can kill the air leakage in the attic, you can make a great dent progress against accelerated air leakage by choking off the leaks in the attic. So again, this was a product that I invented and is patent pending. Spraying on elastomeric. You can brush it on too. So me and this guy, we went up to this attic as a traditional 2,000 square foot ranch house. And we just went up there and the insulation was gone. It was vacuumed. It was ready for air seal. And in 2 days, let's say one day, two guys, one day, we sprayed the whole attic and air sealed it. We tested in, going back to blower door numbers, we tested in at 5,000 cubic feet per minute leakage. That's 5,000 basketball leak per minute at 50 pascals. 50 pascal. That translates to 18 air changes an hour at 50 pascals. That's a freaking leaky building. Not untypical. I did plug some big holes in the attic ceiling, so it's in part of this accounting that didn't get sprayed. After 2 days, two guys air sealing with elastomeric only, no foam. We tested out at 2,400 CFM at 50 pascals. So it came down to 9 air changes an hour, which is a super leaky house. But look, just the attic, we cut down 50% reduction in air leakage. So it shows you they really go for attics, for beginning to air seal your buildings. We can air seal our buildings sequentially. We don't have to do it all at once. We can do the attic in next month, and we can do the crawl space in the year after. And if we ever have to redo the siding, we can redo the siding 12 years after. But we can sequentially build up to make our buildings tighter. We don't have to do it at once, and we can't afford to do it at once. But know what the goals are and the possibilities. And if you air seal, do the killer air seal job while you're there. Don't do a half-assed job and do a Hail Mary and say, well, I hope that works. Tongue and groove. We've all seen this in our buildings. This is very often it's used, most often it's used for roof decks. Sometimes you'll see this in floor material. But T&G typically was used for roof decks as a structural roof deck to walk on and as a finished roof deck, to roof bottom for when you're looking up, you see this nice, pretty solid wood T&G in the living room. But on the roof, it's a structural walking deck. And guess what? See, look at this. So this is particularly bad T&G. So you see that, and you see that and that and that. So these boards, the top plate is like over here somewhere. So these boards are hanging out into the air. So it's an overhang. The top plate's over here. The building doesn't start till back here. So air is going to come in here or go out there. If the heating in the house, heat's going to go up through these grooves, and the heat's going to hit the top of the roof deck, and it probably can't get out if it's tar and gravel or whatever. But the air sure is going to head out this way and go out, exit outside the building, right? It's going to do that, every one of these, right? So that's heat. You're heating the house, and it goes woo right out. How to stop that? Not that difficult, but important. So here's the same roof coming back. Here's the overhang in here. And I didn't do this. I worked with the workers, and I said, here's what you're going to do. I said, go along and drill a hole in every, let me see. So I go back here. Whoop. Oh. I said, drill a hole in every one of these joints over the top plate. So like drill a hole, right, like that. And then drill a hole like that. And then drill a hole like that, all right? To the depth of, drill a hole this deep plus a little bit, all right? So there's the hole. That's how deep the hole is, down. You drill a hole in every T&G joint, and then, so here's what it looks like in the laboratory in the shop. So here's a drill bit coming down, drilling right in the center of the T&G, and that's what it looks like after it's drilled. Wow. So then I said, go back with a caulking gun and inject pressurized caulk, elastomeric caulk into every hole. These were 3/8 holes, right? So what have we done here? Think about it. So here we are injecting caulk into this drilled hole. And then I took the sample piece here, and after the caulk set up, I ran it through a table saw, and whoops, I can't talk this. I ran it and cut off the end so I could see the plug. The caulking was in here, and it came down pressurized, and it's plugged the T&G, right? So air's trying to get out of the building like that, right? It's trying to get out, and it hits these plugs, and it can't. It's right over the top plate of the wall, right? Pretty simple, right? Now you can employ this concept in many parts of the building. You can employ it in floors, from the top side of the floor, from the underside of the floor, from the crawl space, from the inside of the building on T&G. This drill and fill, just keep it in mind and be creative and think of how you can stop air leakage from going inside the house to outside the house by making these plugs. Very simple to make. Essential. So I said, okay, now that you drill all the holes, by the way, were drilled in there. There's a hole in there and in there, right? And the plugs were there. And I said, now we need to make, before we lay on the top sheet of, usually T&G roofs, because of earthquake and structural stuff, you got to put plywood on them anyway, typically. So this roof was going to be, this T&G was going to be recovered with plywood. And knowing that, I said, okay, this is really important. You have to put a gasket. So here's the plywood heading out to the outside of the building, right? I said, you have to put a gasket over the top, over these holes and over the top plate. Because when air comes up from here, right? When air comes up there and hits the bottom of the plywood, it can just continue to run out through that way, right? You know, because things are not flat. It'll go underneath the plywood now. You add a gasket here, and then air can't run out. You're done. You just made that roof airtight. Really important. Leave this gasket out, you're going to get more air leakage. So simple to do. I calculated it took it took about, you could do about 50 feet an hour of this plugging, and then the gasket, I don't know how long. That doesn't take very long. Again, that's for the building. You don't do it, and it will leak for another 60 years until another roof is put on. Here's how you can do the same thing from underneath. Here's T&G running out. This was back in the day when I used to use foam as an air sealant. Drill a hole from underneath outside the building, and then inject foam into the hole, and you make a plug. Same concept, different material. Here's inside the building. Drill up holes drill holes up into there, holes, and then you plug it with caulk, and then you put a trim piece over the holes to cover it. So you just stop. This is that earlier slide where air was blowing in through these holes. You just put a plug up and stop outside air coming in. Saw it here first, people. Up in an attic, T&G, this is brushed on elastomeric. All the joints were brushed on elastomeric. Made a huge difference. This place was unheatable. The woman, it was a small little cabin, and she sat right near the gas heater to eat and to do her work and to hang out, because if she got 4 feet away from the heater, she froze. It was in a dark valley. It was a miserable house. This alone, air sealing, this massive air leak in the ceiling made a huge difference. Again, it's the stack effect. The stack effect in this place was just off the charts. Light cans, well, I'm going to skip this. We all know light cans leak. I'll tell you the fast way around it. Basically, when these LED assemblies came along, they were just total problem solver. Basically, an LED, I've examined a lot of LEDs, and the entire fixture comes with, the light can itself comes with a trim piece on it, right? They're attached. They're kind of, all is one, they're attached, and they're pretty tight. So this light fixture, if you think about it this way, can become a plug in a hole in the ceiling, because the light fixture is pretty airtight. However, I've noticed that the weakness of these light fixtures is the gasket they give you. When you push them up into the ceiling, they can still leak around the untightness of the fitting in the ceiling. They can leak in there, right? In different places, in different times, but they can leak because sometimes it doesn't get pushed up tight. But the rest of this assembly is pretty damn tight. It's tight around there. So what I did was I took this gas stuff called duct seal. It's like putty clay, and you roll it into worms. Take a worm, roll out a worm in the house, put it on there, stick it up into the ceiling. I use a little hair dryer to make it compress more, and then it had this bomb-proof, sticky gasket that holds the can up into the ceiling and is totally airtight. And you take a little butter knife and trim off the excess stuff, and you take a big old hole in any ceiling, put one of these up, and you instantly convert it into a fairly airtight thing. Here's another option. Here's an airtight can. I'll go inside the can, I'll make it airtight in there, reach in, and then take some tape and put tape around between the metal and the drywall, right? And then put a fixture in there. So this, you're air sealing the can from the inside or the attic, and then you're air sealing the opening, which is usually the leakiest part of the can. And this right here would be, I didn't put tape on it so you can see where it would leak, but there would be a gap all around this. So that's tape sealed in. Fireplaces, massive air leakers. I'm going to skip this. We all know that fireplaces are, they're just massive leakers. But big holes in fireplaces and attics. Here's a big hole. The fireplace was decommissioned. You can't do this unless you decommission the fireplace, because code says you're not allowed to put anything combustible against the brick, right? Can't put combustible. But this fireplace was decommissioned from inside the house, but it still left a gap, a massive air leak gap. Sheet foam around it, foam around that for the big gaps, and then elastomeric was smeared on top. Same thing here. Big gap, sheet foam, and then elastomeric around the top.
Terry, just giving you a 10-minute heads up before we'll have to transition to closing.
All right, thanks. So wait, what time is closing?
We'll do closing right around 11:55, 56.
11:55, okay. Okay, hold on. Hold on. Okay. This is my favorite thing to do with fireplaces. Did this, that house that got super airtight, we did this for a lot of reasons. Earthquakes, for air sealing, for insulation, for a lot of reasons. I figured out that in over a 40-year plan, it was much cheaper to take this fireplace out, and for a lot of different reasons. And so I was working for a nonprofit affordable housing, and they decided to go for it. I could show them on paper the value of taking this out and spread out over 40 years in energy savings and indoor thermal comfort. So what kind of caulk? This was some test model. I did for JLC. I wrote some pieces for them. And this one I was testing caulking. There's an article called Air Sealing Without Foam. But I tested a lot of caulks, and basically I found out that elastomeric was the kind to use. Since we're running low on time, these are the properties of elastomeric. Water-based, easy cleanup. I think I've gone over this. Elastomerics are just the way to go. When you're buying caulks, on the side of any 2 bucket of elastomeric, it gives you the VOC ratings. You can also get the MSDR, the material safety data sheets, or the data sheets on any material, and look it up and see what you're using. You can use that sheet and show it to your homeowner and say, hey, you know what? We don't use this stuff because it's got 70 grams per liter of VOC. We use this stuff. It's got 12 grams per VOC. And they might say, great, thanks a lot. Or they might ask for low VOC air sealing stuff. And if you stick with elastomerics, you're going to definitely be in the zone for low VOC. This is an important slide. So if you don't have to use tape to plug a lot of wires, you can use caulk. This is super elastic caulk. Again, it's that sticky stuff up right here. It's that really sticky stuff was injected into these holes. And so what's important to do, if you're filling multiple wires in a hole, foam will definitely not do the job. It won't. It will do some, and it will fail a lot. So what you do is you stick the caulking gun deep into the hole, and you inject it. You pressurize the caulk into the hole, and then you pull it out, and you stick it into another part of the hole between the wires, and you inject it, and you wiggle the wires, and you pull it out, and you stick it. You keep taking the gun in and out, injecting it until you're fully satisfied. By wiggling the wires, you're satisfied that it has fully embedded and surrounded all those wires with this perpetual sticky stuff. That is bomb-proof air sealing. For all of these wires, what do you guess? 12 wires, it took about 3 minutes for 80-year air sealing for these. And foam would have just been a total crap job, guaranteed. Here's tape sealing, electrical stuff. You can see I like tape sealing. There's not always money on the job for that. Here's the ability for one metal electrical box to leak outside into inside. And here's that metal box tape sealed. All of these leaks here, gone to this. Tape sealing up in an attic, expensive work. More electrical boxes. These are airfoil.com, airtight electrical boxes, my favorite kind. There's different kinds. I happen to like these. If we have more time, I could explain where to get them and how they work. So if you're going to go around and air seal from the inside, it's just like a Hail Mary, like weatherization. You just want to make a place tighter inside without, you don't have access to any leaks. Individual outlets can work. It definitely works better than not doing it. But again, if you have air sealing mind, see this gasket right here, this one, right? That's like a Home Depot, 12 for $1 kind of gasket for outlet place, right? But this won't really do the job. So look at the thickness of this, right? That's the thick. Look at the thickness of this gasket, right? If you put this gasket over a cover plate, it will seal all around the outlets. It'll stop this leak. That gasket will stop this leak. The skinny one may or may not, right? And how often does this happen in houses? Sometimes, right? Also, so here's a straight edge across a thin gasket, and it shows the ability to air leak underneath the gasket. And if this corner is not tight on the drywall, like here, it's going to leak out anyway. It's a waste of time. So here's a thick gasket placed over one. Even this is not airtight. This is not airtight. Air can't get out. This is the gasket company that makes that thick one. So look at the thickness of cover plate gaskets. Puddle sealing on a vertical plane. What do we got? 3 minutes left? Yeah, was that a nod?
Just about.
Just about. Okay. Okay, I'll just do puddle sealing. Puddle sealing is something that I think I coined the phrase. We're up in an attic. Here's a drywall ceiling. Here's floor joist, ceiling joist over here. I just took some scrap wood and made a dam from across to the joist, and then flooded this this dam with this happened to be Fixall. But look what happens when you flood it. You can see this stuff all around the wires, right? You can see it's flooding. That's air sealing. You spray that with foam. Foam is not going to air seal in a lot of these conditions. But that's basically what puddle sealing is. So what I used in that particular patch was I used Fixall Presto patch. I mixed fiberglass shredded insulation in with it to give it some body and sturdiness, and flooded it. What I do more now is I use a combination of, I might just use elastomeric instead of Fixall. Fixall is a cheap, fast way. I mean, to dam this up and flood it is pretty darn cheap in an attic. So here's puddle sealing conduit. Here's multi-wires coming out of conduit, right? So again, you can stuff these tubes here with foam, gun foam, or I now use denim, and then after you're confident the liquid won't run through the conduit, you can puddle seal on top of them and air seal multiple wires. I'm going to show you a demonstration here. So this might be the last thing we look at. So here is an example of, oh, actually, no, I have this better in a slide. Never mind. We may not get to that. I feel a little rushed here, but what the hell. Okay, this will be the last slide. So what this is about is what I call liquid elastomerics. And it looks like a tube of caulking, but what they are indeed is they have the ability to flow. They have a higher viscosity. And if you put it in a puddle, it will puddle out, right? If you put the elastomeric in this hole, it'll just turn into a lake and puddle all around the wires. See where that's puddled all around that, right? And this is to stop the puddle from dripping through the whole conduit. So here's the brands for that. These are elastomerics, a little less VOC. These Sikaflex, we all heard that one. This is used mostly for concrete masonry work. So I think we should stop there because we're out of time. And we may just go back to this if you return and just pick up where we left off. Okay, is that good, Ian?
Yeah, excellent. We'll pick up where we
too
left
exciting,
off.
too much fun. You know, I have to have a disclaimer. As I said, that this learning, are we gone or still there?
Still there.
Oh, yeah, I have to say that this learning, you know, like most learnings, it takes, you know, I'm trying to put down 12 years worth of air sealing, experimenting, learning, and working into 2-3 hour sessions. And it's it's complicated, you know, it's so complex when you get into it. And it's frustrating for me to try and deliver you the big message in a few sessions. But if you keep in touch with me or 3CREN, they'll have a copy of my book, I'm sure. You can get this in a more slower, detailed way. Maybe, I'm guessing in 3 months, it might be ready for publish. So thank you for coming here, and I hope you come back to the next one. The next one is some equally important details we need to know about air sealing buildings. So hope to see you next time. Thanks.
Thank you, Terry. If you can all please complete the quick poll that we have on the screen, we really appreciate it. And like Terry mentioned, make sure you come back next Thursday. We have part 2 of the session. It was very interesting, and the pictures are very engaging and very descriptive. So we're definitely interested in part 2. Please come back and join us for that. And then also be on the lookout in your inbox for if you register for your AIA credits, you will receive those also in your inbox. And please give us any feedback, any suggestions for further topics, or anything else that you're interested in, information about 3CREN, or just in general, what other topics you would like for us to be able to offer you. Once again, this is info@3cren.org. And before you exit, please complete the poll. And thank you for joining us.
Can I add one more comment, please?
Yeah.
Oh yeah, that I want to reiterate and remind you that these trainings, these offerings are so valuable and so rare that take a day off or half a day off and learn this stuff. What you learn in 3 hours or 4 hours will stick with you and improve your game for the rest of your building world, the rest of your life. So please take the time to tune into 3CREN's offerings. They're very valuable courses. Okay, thanks.
Thank you.
Tell a friend.
Thank you, Terry.
You're welcome. Is the mic still on? Can we hear each other? Are we
Mike's
on?
still on. Yeah,
Oh, so Ian, can everybody hear us?
they can until they exit. Yes.
Okay, I just wanted to check in with you later and see I want to get your poll.
Okay.
But so can we, I don't have your phone number. You want to
Yeah,
email it to me?
We can reconvene. I'll email you my phone number and we can.
All right, great. Yeah, I
reconvene.
want to check in with you and see what you think.
All right.
Thank you very much.
Thank you, everyone.
Thank you.